There is a star in the night sky that is breathing. Not in the way a candle flickers when a draft crosses the room. Not in the way the moon seems to dim when a thin cloud slides over its face. This star, a real physical ball of plasma hotter than anything on Earth, is swelling outward and then contracting back inward, over and over, like a slow, titanic heartbeat made of fire and gravity. Its surface rises by millions of kilometers, then falls again. Its temperature shifts by hundreds of degrees. Its light brightens, dims, brightens again. And it has been doing this, without stopping, for longer than human civilization has existed. The star is called Delta Cephei. It sits roughly 880 light-years from Earth, in the northern constellation Cepheus. And in 1784, a young English astronomer named John Goodricke, remarkably, only 21 years old and profoundly deaf since childhood, noticed something about it that nobody else had caught. Its brightness was changing, not randomly, not chaotically. It was pulsing with a rhythm so precise you could set a clock by it. Every 5 days, 8 hours, and 47 minutes, the star completed one full cycle of brightening and dimming. Then it did it again, and again, and again. Goodricke reported the discovery to the Royal Society of London. He was awarded the Copley Medal for his contributions to astronomy. He died just 2 weeks later, at the age of 21, likely from pneumonia contracted during his long nights of observation. He never knew what he had found. He never imagined that the pulsing light of Delta Cephei would one day hand humanity the most powerful distance-measuring tool in the history of science, a tool that would settle the raging debate about whether our galaxy was the entire universe or merely one tiny island in an ocean of hundreds of billions, a tool so reliable that astronomers would use it to push their measurements outward across 30, 40, 60 million light-years of empty space, a tool that right now, in this very decade, is sitting at the center of a crisis so severe that it threatens to crack open the foundations of modern cosmology itself. Two teams of scientists, using two completely different methods, have measured the expansion rate of the universe. Their answers do not match. The discrepancy is enormous. And the Cepheid distance ladder, built on the pulsations that Goodricke first noticed, is one of the measurements that refuses to budge. And that tool is nothing more than a pulsing star. More than 100,000 variable stars have been identified and catalogued. They span every corner of the Milky Way and have been detected in galaxies millions of light-years away. Some pulse in hours, some pulse in days, some pulse in cycles lasting more than a year, and collectively they form the backbone of one of the most important measurement systems in all of science, the cosmic distance ladder. Without them, we would not know how far away other galaxies are. We would not know the expansion rate of the universe. We would not know how old the observable cosmos is. Everything we think we understand about the large-scale structure of reality depends, in one way or another, on the pulsation of variable stars. Here is what makes this story truly staggering. There are stars that change brightness because something passes in front of them, an orbiting companion, a disk of dust, a transiting planet. There are stars that flare violently because of magnetic eruptions on their surfaces. But pulsating variable stars are different. They change because the star itself is unstable. The entire outer envelope of the star is heaving in and out, driven by a mechanism so elegant and so deeply counterintuitive that it took physicists nearly a century to figure out how it worked. And when they finally did, they discovered that the pulsation was not a flaw, it was not a defect, it was a message. Encoded in the rhythm of that pulsation, in the precise length of the cycle, in the shape of the light curve, in the ratio of rise time to fall time, is information about the star's true brightness, its intrinsic luminosity, the raw power output of its nuclear furnace. And if you know how bright a star truly is, and you can measure how bright it appears from Earth, you can calculate exactly how far away it is. That is the breakthrough, a beating heart that announces its distance from across the cosmos. But this story does not end with distances. It does not end with maps or measurements or even the size of the universe, because in the last 2 decades, scientists have discovered that pulsating stars carry an even deeper kind of information, not just about how far away they are, but about what is happening inside them. The frequencies at which a star vibrates, the overtones it produces, the subtle splittings and modulations in its oscillation pattern, All of this encodes the star's internal structure, its core rotation, its chemical composition, its temperature gradient, the way energy flows through its layers. We can listen to a star the way a doctor listens to a heartbeat, and from the sound, diagnose what is happening in the interior. This science is called ostaseismology, and it has already overturned things we thought we knew about how stars work. The cores of red giant stars are spinning far more slowly than our models predicted. The mixing of elements inside massive stars is more vigorous than we assumed. The very structure of the Sun, the one star we know best, does not perfectly match our calculations. By the end of tonight, you are going to understand how a handful of flickering stars gave us the size of the universe. You are going to see how a woman working in a basement at Harvard, denied the right to even use the observatory's main telescope, made a discovery so profound that it redrew the map of everything. You are going to learn why the same stars that solve the greatest question in astronomy are now at the center of its greatest unsolved problem. A disagreement so deep that some physicists believe it could require entirely new physics to resolve. And you are going to discover what it means that the nearest, brightest Cepheid variable in the entire sky, the North Star itself, Polaris, recently did something that no one expected and no one can fully explain. There is one number in this story that broke physics. It comes from a measurement so simple it should have been settled decades ago. And yet, today, two of the most precise instruments ever built disagree on its value by an amount that exceeds the threshold physicists use to declare a genuine discovery. One instrument measured the earliest light in the universe. The other measured the pulsation of Cepheid stars. They should agree. They do not. And the gap will not close. We will get to that number. But first, you need to understand the stars. You also need to understand something about how we see the cosmos. Every measurement of the size, age, and expansion rate of the universe, everything we think we know about how large the observable cosmos is and how fast it is growing, traces back, ultimately, to our ability to measure distances. And our ability to measure distances across millions of light years traces back, more than any other single method, to the pulsation of variable stars. Take away the Cepheids, and the distance ladder collapses. Take away the distance ladder, and modern cosmology loses its foundation. That is how much depends on this one phenomenon, a star breathing in and out. This is not a story about dots of light in the sky. This is the story of how the universe learned to speak, and how a few brilliant, stubborn, sometimes overlooked minds finally learned to listen. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand why variable stars matter, why they are not merely a curiosity, but one of the most consequential phenomena in all of astrophysics, you first have to understand a problem that haunted astronomy for centuries. And that problem was simple, devastating, and for most of human history completely unsolvable. We had no idea how far away anything was. Think about that for a moment. For thousands of years, human beings looked up at the night sky and saw thousands of points of light. They mapped those lights into constellations. They named them. They built entire systems of mythology, navigation, and agriculture around their positions and their risings and settings. But they could not answer the most basic question of all. How far away are they? Is that bright star nearby and intrinsically dim, or is it enormously distant and blindingly powerful? Is that faint star a weak ember close at hand, or a raging furnace glimpsed from an unimaginable distance? You cannot tell just by looking. A candle held at arm's length can appear the same brightness as a bonfire seen from a hilltop. Without knowing which one you are looking at, you are completely lost. Distance and brightness are tangled together in a knot that observation alone cannot untie. This is the fundamental problem of cosmic distance, and it is not an abstract puzzle. It is the wall that separated humanity from understanding the true scale of the universe for millennia. The first real crack in the problem came from an old surveying trick, parallax. If you hold your thumb out in front of your face and close one eye, then switch eyes, your thumb appears to jump against the background. That apparent shift is parallax. And it works because your two eyes are separated by a small distance, roughly 6 to 7 centimeters. The size of the shift, combined with the distance between your eyes, lets you calculate how far away your thumb is through simple trigonometry. Now scale that up enormously. The Earth orbits the Sun. 6 months apart, it sits on opposite sides of an orbit, roughly 300 million kilometers across. A baseline vastly larger than the distance between your eyes. If you photograph the same star from opposite sides of Earth's orbit, a nearby star should appear to shift slightly against the background of more distant, effectively motionless stars. That shift, the parallax angle, tells you the distance. The smaller the angle, the farther the star. The idea had been understood since antiquity. The ancient Greek astronomer Aristarchus proposed a heliocentric model of the solar system and understood that if the Earth moved, stellar parallax should be observable. But he could not detect it. Neither could Tycho Brahe, the greatest naked-eye observer in history, who used the absence of detectable parallax as an argument against the heliocentric model. The shift was simply too small. The nearest star to the Sun, Proxima Centauri, sitting 4.24 light-years away, has a parallax angle of just 0.76 arcseconds. That is roughly the width of a coin seen from 4 kilometers away. For centuries, telescopes simply were not precise enough to measure it. The breakthrough came in 1838. Friedrich Wilhelm Bessel, a German astronomer and mathematician working at the Königsberg Observatory in what is now Kaliningrad, Russia, used a precision instrument called a heliometer, a telescope with a split lens that could measure tiny angular separations to detect the parallax of a star called 61 Cygni. The shift he measured was 0.314 arcseconds, corresponding to a distance of roughly 10.3 light-years. For the first time in human history, a person had measured the actual distance to another star. It was a monumental triumph, but it was also, almost immediately, a wall. Parallax works beautifully for nearby stars. Within a few hundred light-years, the angles are large enough to measure with ground-based telescopes. Push to a few thousand light-years, and the precision required becomes extreme. The angles shrink to thousandths of an arcsecond. Push to 10,000 light-years, and the shift becomes so vanishingly small that even the finest instruments of the 19th and early 20th century could not detect it. The European Space Agency's Hipparcos satellite, launched in 1989, pushed reliable parallax measurements out to roughly 1,000 light-years by operating above the blurring atmosphere. The Gaia spacecraft, launched in 2013, has extended this reach dramatically, providing accurate parallaxes for more than 1 billion stars, some as far as tens of thousands of light-years away, by measuring positions with micro-arc-second precision from a stable orbit around the Sun. But even Gaia has limits. The Milky Way spans roughly 100,000 light-years across. Other galaxies sit millions, hundreds of millions, billions of light-years away. No parallax measurement, no matter how precise, can reach them directly. So for most of the history of astronomy, scientists could measure the distances to their nearest stellar neighbors, and nothing else. They could see the light from billions of stars, from nebulae, from the mysterious spiral structures that some suspected were other galaxies. But they could not say how far away those objects were. The universe beyond a few thousand light-years was, in terms of distance measurement, a complete void. Imagine a map maker who can measure distances within a single city block, but has no way to determine how far it is to the next city, let alone the next continent, let alone the other side of the planet. That was the state of astronomy in the late 19th century. Scientists could argue about whether the Milky Way was 10,000 or 100,000 light-years across, and no one could produce a definitive number. They could argue about whether the faint spiral nebulae visible through the largest telescopes were small gas clouds within our galaxy, or entire separate galaxies, lying at almost incomprehensible distances, and no one had the evidence to decide. The greatest telescope in the world could gather more light, resolve finer detail, but it could not, on its own, tell you how far away anything was. Distance was the locked door, brightness was the keyhole, and variable stars, it would turn out, were the key. And then, in a basement workroom at the Harvard College Observatory, something extraordinary happened. Her name was Henrietta Leavitt. Born on the 4th of July 1868 in Lancaster, Massachusetts, she was the daughter of a Congregational minister. She attended what was then called the Society for the Collegiate Instruction of Women, later renamed Radcliffe College, where she excelled in classical Greek, fine arts, philosophy, analytical geometry and calculus. In her senior year, she took an astronomy course that ignited a fascination she would carry for the rest of her life. In 1893, Leavitt took a position at the Harvard College Observatory under the direction of Edward Charles Pickering. She was not hired as an astronomer. Women were not permitted to hold that title. She was hired as a computer, one of a group of women, later called the Harvard Computers, whose job was to examine photographic plates and catalogue the positions, brightnesses, and spectral characteristics of stars. The work was painstaking, tedious, meticulous, and intellectually demanding in ways that received almost no recognition. Leavitt was paid 25 cents an hour, roughly $7 in today's currency. But Leavitt had something that no salary could measure and no title could confer. She had an extraordinary eye for pattern. She could look at hundreds of tiny dots on a glass photographic plate and detect variations that others missed. And Pickering assigned her to study a specific set of plates, images of the Small Magellanic Cloud, a small, irregular companion galaxy visible from the southern hemisphere, sitting roughly 200,000 light-years from Earth. The Small Magellanic Cloud was critical for one simple but powerful reason. All the stars within it were at roughly the same distance from us. The cloud itself is small compared to the distance separating it from Earth. So the difference in distance between a star on the near side and a star on the far side is negligible. This means that if one star in the cloud appeared brighter than another, the difference was not caused by one being closer. It was because that star was genuinely, intrinsically more luminous. The Small Magellanic Cloud provided what astronomers desperately needed: a laboratory where apparent brightness was a faithful proxy for true brightness. Leavitt began cataloguing variable stars within the cloud, stars whose brightness changed over time in regular, repeating patterns. She had already identified more than 1,000 variable stars in the Magellanic Clouds by 1908. But in that year, she published a preliminary finding that hinted at something remarkable. Among the Cepheid-type variables, there seemed to be a correlation. The brighter ones had longer periods. She spent the next 4 years refining the result. In 1912, she published a short, elegant paper, formally credited to Edward Pickering, though the first sentence stated it was prepared by Miss Leavitt, presenting data on 25 variable stars in the Small Magellanic Cloud. The data were plotted on a graph, the logarithm of the period on one axis, the apparent magnitude on the other, and the result was unmistakable. The points fell along a straight line. The brighter the star, the longer its pulsation period. In Leavitt's own words, a straight line can be readily drawn among each of the 2 series of points corresponding to maxima and minima, thus showing that there is a simple relation between the brightness of the Cepheid variables and their periods. That single sentence is one of the most important ever written in the history of science. Here is why. If the period of a Cepheid's pulsation tells you its luminosity, its true intrinsic brightness, then you have a standard candle. The concept is simple but incredibly powerful. Imagine you know that a particular type of lamp always produces exactly 1,000 watts of light. If you see that lamp from across a dark plane and it looks dim, you know it must be far away. If it looks bright, it must be close. By measuring the difference between the lamp's known wattage and its observed brightness, you can calculate the exact distance using the inverse square law. The fact that brightness drops as the square of the distance. Leavitt's period luminosity relation turned every Cepheid variable in the universe into such a lamp. Measure the period. The period gives you the luminosity. Compare the luminosity to the apparent brightness. Calculate the distance. The method is elegant, powerful, and, crucially, it works across immense distances. Cepheids are supergiant stars, enormously luminous, thousands to tens of thousands of times brighter than the sun. They can be seen in galaxies tens of millions of light-years away. In one stroke, Leavitt had punched through the distance barrier that had imprisoned astronomy since its beginning. But Leavitt herself never saw the full impact of what she had done. She continued her work at Harvard, earning modest recognition from her peers. The Swedish mathematician Gösta Mittag-Leffler learned of her work and attempted in 1926 to nominate her for the Nobel Prize, only to discover that she had died on December 12, 1921, of stomach cancer. She was 53 years old. The Nobel Prize cannot be awarded posthumously. The woman who gave humanity the key to measuring the universe was buried in Cambridge, Massachusetts, in a family plot, and for decades her name appeared mainly in footnotes and acknowledgements. The world she unlocked, however, was about to explode open. In the years immediately following Leavitt's discovery, astronomers raced to calibrate her period luminosity relation, to convert it from a relative scale to an absolute one. To do this, you needed to know the actual distance to at least one Cepheid variable, so you could anchor the relationship and convert measured periods into true luminosities. In 1913, just 1 year after Leavitt's publication, the Danish astronomer Ejnar Hertzsprung applied statistical parallax methods to estimate the distances to several Milky Way Cepheids and used them to calibrate the 0 point. His first distance estimate for the Small Magellanic Cloud was roughly 30,000 light-years, too small by almost an order of magnitude, but it was a beginning. Then came Harlow Shapley, one of the most ambitious and controversial figures in early 20th century astronomy. Working at the Mount Wilson Observatory in California with access to the powerful 60-inch reflector, Shapley identified Cepheid variables and RR Lyrae stars inside globular clusters, the dense, spherical swarms of hundreds of thousands of old stars that orbit the Milky Way like satellites. By measuring their periods and using Leavitt's law, Shapley calculated distances to dozens of globular clusters, and what he found reshaped the picture of our galaxy. The Sun was not at the centre of the Milky Way. It was off to one side, roughly 2/3 of the way from the centre to the edge. The galaxy was far larger than most astronomers had believed, stretching tens of thousands of light-years across, with the globular clusters forming a vast halo around it. Shapley's work, powered directly by Leavitt's law, demolished the old, comfortable picture of the Milky Way as a modest, sun-centered system. The galaxy was enormous, and we were not at its heart. But Shapley also made a critical error of judgment that would haunt him. He became so convinced of the Milky Way's vastness that he argued it was the entire universe. The faint, fuzzy spiral patches visible through the largest telescopes, what some astronomers called spiral nebulae, were, Shapley insisted, merely gas clouds within our own galaxy. They could not be separate galaxies, he argued, because his new, enlarged Milky Way was big enough to encompass them. He was wrong, and the man who proved him wrong would use the same tool to do it. In 1920, Shapley debated this point publicly with Heber Curtis of the Lick Observatory in what became known as the Great Debate, one of the most famous confrontations in the history of science. Shapley argued for one large galaxy containing everything. Curtis argued that the spiral nebulae were island universes, separate galaxies comparable to the Milky Way, lying at vast distances. Neither man had decisive evidence. The debate ended without resolution, and then, in October of 1923, the resolution arrived on a single photographic plate. Edwin Hubble, a meticulous and ambitious astronomer working with the 100-inch Hooker telescope at Mount Wilson, then the most powerful telescope in the world, turned it toward the Andromeda Nebula, the largest and brightest of the spiral nebulae. He was searching for novae, stars that temporarily brighten by many magnitudes. On October 5th, he identified a candidate on a photographic plate and marked it with the letter N. But as he tracked the object over subsequent nights and compared its brightness to earlier plates, he realized something that changed his life and the history of science. It was not a nova, it was a Cepheid variable. He crossed out the N and wrote VAR with an exclamation mark that has become one of the most famous punctuation marks in scientific history. Using Leavitt's period luminosity relation, Hubble measured the Cepheids period and calculated its distance. The number that came back was staggering. The Andromeda Nebula was roughly 900,000 light-years away. Even with the flawed calibration of the day, a calibration that would later be corrected upward. This placed Andromeda far beyond the boundaries of the Milky Way. It was not a gas cloud inside our galaxy. It was an entirely separate galaxy, a vast island universe containing billions of its own stars. In a single observation, the known universe expanded beyond all previous imagination. The Milky Way was not everything. It was one galaxy among what would eventually turn out to be hundreds of billions, stretching across a cosmos so vast that light itself requires billions of years to cross it. If you could somehow freeze time and start driving a car at highway speed from one edge of the observable universe to the other, you would need to drive for more than 1 trillion years. Every star in the sky would burn out, cool, and die long before you were even a fraction of the way there. That is the scale of what Hubble had revealed, and the measuring tape he used was a pulsating star. Hubble's announcement, when it was formally accepted by the astronomical community following his publication in 1925, ended the great debate decisively. The spiral nebulae were indeed separate galaxies. Shapley, for all his brilliance in mapping the Milky Way, had been wrong about its being the whole universe, and Curtis, who had argued for island universes, was vindicated, though the distances turned out to be far greater than even he had imagined. And the key that unlocked this revelation was a pulsing star, interpreted through a law discovered by a woman who was paid 25 cents an hour to stare at glass plates in a basement. But the revolution had only just begun. Within a few years, Hubble measured Cepheid distances to other galaxies and combined those distances with measurements of how fast each galaxy was receding. Using the redshift of spectral lines, the Doppler effect applied to light. When a galaxy moves away from us, its light is stretched to longer wavelengths, shifting toward the red end of the spectrum. The faster the recession, the greater the redshift. The American astronomer Vesto Slipher had already measured redshifts for dozens of spiral nebulae by the early 1920s, finding that most were moving away from us at impressive speeds, some exceeding 1,000 kilometers per second. But Slipher could not determine how far away they were. Hubble could, and when he plotted distance against recession speed, the result was unmistakable. Every galaxy was moving away from us, not just some, all of them. And the farther a galaxy was, the faster it was receding. The relationship was linear: double the distance, double the recession speed; triple the distance, triple the speed. This was Hubble's law, published in 1929. One of the most consequential papers in the history of physics. It was the observational foundation for the expanding universe. The discovery that space itself is stretching, carrying galaxies apart like raisins in a rising loaf of bread. This expansion had been predicted theoretically by the Belgian physicist Georges Lemaitre in 1927, based on solutions to Einstein's equations of general relativity. But Hubble provided the data that made it undeniable. The universe was not static. It was not eternal and unchanging. It was expanding, and if you ran the expansion backward in time, everything must have once been closer together, compressed into an unimaginably hot, dense state. This realization was the seed of what would become the leading scientific model for the origin of the observable universe. And this entire chain of reasoning, Lemaitre's theory, Hubble's observations, the expanding cosmos, the hot, dense early state, rested, entirely and directly, on Cepheid distance measurements, which rested on Leavitt's period luminosity relation, which rested on the simple observation that some stars pulse. From a heartbeat to the expansion of the cosmos, from a glass plate in a basement to the shape of the universe. That is the power of variable stars. A single empirical relationship. Period predicts luminosity. Bridge the gap between human experience and cosmic reality. A star flickering in the night sky, observed with patience and decoded with mathematics, told us that we live in an expanding universe of staggering immensity. There may be no more powerful example in all of science of how a small, precise observation, made by someone with no political power and no institutional standing, can reshape the entire framework of human knowledge. But understanding that power requires understanding why these stars pulse. What is happening inside them? What physical mechanism drives a supergiant star to swell and shrink with such clockwork precision, repeating the same cycle to within seconds over spans of years and decades? Because if we do not understand the mechanism, we cannot fully trust the tool. And the answer, when it finally came after decades of theoretical struggle, turned out to be one of the most beautiful and surprising pieces of physics in the history of stellar astrophysics. Every star is a battleground. Gravity pulls inward with relentless, crushing force, trying to collapse the star into a point. Radiation pressure pushes outward, generated by the thermonuclear furnace in the core, where hydrogen is fused into helium at temperatures of tens of millions of degrees. In a stable star like the Sun, these two forces are in near-perfect balance, a condition called hydrostatic equilibrium. The inward pull of gravity exactly matches the outward push of radiation and gas pressure at every depth. The star neither expands nor contracts, it simply burns steadily for billions of years. But not all stars are in perfect balance. Some stars, through the course of their evolution, as they age and change and their internal structures shift, wander into a region of the Hertzsprung-Russell diagram that astronomers call the instability strip. This is a narrow vertical band running through the upper portion of the diagram, populated by stars with surface temperatures between roughly 6,000 and 10,000 degrees Kelvin. Stars that enter this strip become unstable. They begin to pulsate. The mechanism that drives the pulsation is called the kappa mechanism, named after the Greek letter kappa, which represents the opacity of stellar material, the degree to which that material blocks the passage of light. And the way it works is breathtaking in its elegance. Deep inside a pulsating star, there exists a layer where helium is in a partially ionized state. Specifically, where helium atoms are in the process of losing their second electron, transitioning from singly ionized to doubly ionized helium. This is called the second helium ionization zone, and it sits at temperatures of roughly 40,000 to 50,000 degrees Kelvin. In most stellar material, when you compress a gas, it gets hotter, and hotter gas becomes more transparent. Its opacity drops. Radiation streams through more easily, the pressure decreases, and the compression naturally damps itself. The star self-corrects. Any pulsation tendency is suppressed. But in the partially ionized helium zone, something remarkable happens. When the gas is compressed, the extra energy does not go into making the particles move faster. Instead, it is absorbed by the ionization process itself, stripping away that second electron from helium atoms. The temperature barely rises, but the density increases. And because the temperature stays nearly constant while the density goes up, the opacity of the heavier trace elements in this layer actually increases. The layer becomes more opaque, not less. This is the crucial inversion. The compressed layer traps radiation. Energy builds behind it like water behind a dam. Pressure increases. The layer is shoved outward. The star expands. As it expands, the helium layer cools, atoms recombine, opacity drops, radiation escapes freely, pressure falls, and gravity pulls the layer back inward. The cycle repeats. Expand, contract, driven by a thin shell of helium acting as a valve. Arthur Eddington, the great British astrophysicist, proposed this valve-like mechanism in the 1920s, calling it a stellar heat engine. The detailed identification of the helium ionization zone as the driver came in the 1950s and 60s through work by Sergei Zhevakin in the Soviet Union and John Cox and his colleagues in the United States. But the essential picture is stunning. A star pulsates because one thin layer inside it behaves in exactly the wrong way, at exactly the right moment, to sustain an oscillation that would otherwise die away. And this is why the instability strip is narrow. If the star's surface is too hot, the ionization zone sits too close to the surface, in a region dominated by convection where the kappa mechanism cannot operate. If the surface is too cool, the ionization zone is buried too deep, where the pulsation energy cannot effectively penetrate. Only within a specific temperature range, roughly 1,000 degrees wide, does the zone sit at precisely the right depth, and the star begins to breathe. Think about what this means. Out of the tens of billions of stars in a galaxy, only those that happen to pass through this narrow temperature window will pulsate as Cepheids. It is like a cosmic lottery, and the prize is visibility, because Cepheids are supergiants, among the most luminous stars in existence. Those that land in the instability strip become beacons visible across enormous distances. A typical classical Cepheid is between 1,000 and 100,000 times as luminous as the Sun, depending on its period. A Cepheid with a period of 50 days can be seen in galaxies 40 or 50 million light-years away with the Hubble Space Telescope. These are the most distant individual stars that astronomers routinely observe and identify. The period luminosity relation itself has been refined enormously since Leavitt's original 25 stars. Modern calibrations use thousands of Cepheids observed in multiple wavelengths, visible light, near-infrared, mid-infrared, to minimize the effects of interstellar dust, which absorbs and scatters light and makes stars appear dimmer and redder than they truly are. Observations in the infrared are particularly valuable because dust affects infrared light far less than visible light. The Spitzer Space Telescope, before its retirement, provided crucial infrared photometry of Cepheids in the Milky Way and the Large Magellanic Cloud, tightening the calibration of the Leavitt law to a precision of better than 2%. And the Cepheids are not alone on the instability strip. At lower luminosities, sitting on the horizontal branch of the Hertzsprung-Russell diagram, are the RR Lyrae variables. These are ancient stars, among the oldest in the galaxy, typically around 10 to 12 billion years old, according to scientific estimates. They have masses of roughly 0.6 to 0.7 times the mass of the Sun. They have already exhausted the hydrogen in their cores, ascended the red giant branch, undergone a violent event called the helium flash at the tip of the red giant branch, and settled onto the horizontal branch, where they burn helium in their cores and hydrogen in a surrounding shell. Those that land within the instability strip become RR Lyrae pulsators. RR Lyrae stars pulsate with shorter periods than Cepheids, typically between 0.2 and 1 day, and they have a remarkable property. Their absolute luminosity is nearly constant, at roughly 50 times the luminosity of the Sun, regardless of their period. This makes them excellent standard candles for a different regime of distances, while Cepheids are the rulers for measuring extragalactic distances. Reaching into other galaxies, RR Lyrae stars are the rulers for measuring distances within our own galaxy. They are found in abundance in globular clusters, in the galactic halo, and in nearby dwarf galaxies. Every globular cluster that contains RR Lyrae stars becomes a point of known distance, and the three-dimensional structure of the Milky Way's halo has been mapped primarily using them. Below the RR Lyrae stars on the instability strip sit the delta Scuti variables, stars of about 1.5 to 2.5 solar masses, pulsating with periods measured in hours rather than days, and extending upward from the Cepheids at the highest luminosities are even more exotic pulsators. The RV Tauri variables, supergiants with long periods and alternating deep and shallow brightness minima, and the slowly pulsating B stars and beta Cephei stars, which are driven not by the helium ionization zone, but by opacity changes in ion group elements deep in their interiors. The instability strip is not a single mechanism, but a family of related phenomena, united by the principle that certain layers inside certain stars trap and release radiation in a way that sustains oscillation. And every type of pulsator, Cepheids, RR Lyrae, delta Scuti, W Virginis, BL Herculis, RV Tauri, tells a different part of the story of stellar evolution. Their pulsation periods, amplitudes, and light curve shapes encode information about mass, radius, luminosity, temperature, chemical composition, and evolutionary stage. They are not mere distance markers. They are diagnostic tools for understanding how stars live and die. This single mechanism explains the Cepheids. It explains the RR Lyrae stars. It explains a whole menagerie of pulsating variables stretching across the Hertzsprung-Russell diagram. Each type occupies a slightly different region of the instability strip, pulsates at a different rate, and carries different information about its mass, evolutionary stage, and distance. But there is something even deeper hiding in the pulsation, something that would not be fully appreciated until the Space Telescope era. The pattern of oscillations in a star, not just the main period, but the overtones, the frequency spacings, the subtle modulations, carries information about the star's internal structure, in the same way that the overtones of a struck bell encode the bell's shape, thickness, and material composition. Consider an analogy. If you strike a wine glass with a spoon, it rings at a specific pitch. That pitch depends on the glass's size, shape, thickness, and what it is made of. A crack in the glass changes the sound. A chip in the rim changes it. Fill the glass with water, and the pitch drops. You can learn about the glass by listening to it. Stars work the same way, but the information they carry is incomparably richer. A pulsating star does not vibrate at a single frequency. It vibrates in multiple modes simultaneously, some radial, with the entire star expanding and contracting symmetrically, and some non-radial, with different parts of the surface moving in different directions. The pattern of these modes, their frequencies, their spacings, their amplitudes, is a fingerprint of the star's interior, its density profile, its temperature gradient, its core composition, its rotation rate, its age. This idea has a name: astroseismology. It was born from the study of the sun, helioseismology, which began in the 1960s and 70s, when astronomers discovered that the sun's surface oscillates with millions of distinct frequency modes, each corresponding to a different acoustic wave bouncing through the solar interior. By analyzing these modes, helioseismologists map the internal structure of the sun with astonishing precision, determining the depth of the convective zone, the rotation profile as a function of latitude and depth, and the sound speed throughout the interior. The agreement between helioseismic measurements and theoretical solar models was one of the great triumphs of 20th century astrophysics, and the small discrepancies that remained pointed the way to the resolution of the solar neutrino problem, confirming that neutrinos have mass. Extending astroseismology to other stars required space-based photometry of extraordinary precision because the oscillation amplitudes of sun-like stars are tiny, just a few parts per million in brightness. That capability arrived with the CoRoT satellite, launched by the French and European space agencies in 2006, and then in dramatic fashion with the Kepler Space Telescope in 2009. What these missions revealed about stellar interiors would overturn assumptions that had stood for decades. But that revolution is a story for a later section. For now, the critical point is this: variable stars are not a single phenomenon. They are a vast and interconnected web of stellar physics, spanning the entire Hertzsprung-Russell diagram, encoding distances, internal structures, chemical abundances, and evolutionary histories. They are the Rosetta Stone of stellar astrophysics. And the more we learn to read them, the more we discover that the universe is more complex, more surprising, and more deeply strange than we ever imagined. But before we get to those surprises, we need to confront something deeply troubling. Because the very tool that Leavitt gave us, the Cepheid distance ladder, is now at the heart of a crisis that has been growing for more than a decade, that has resisted every attempt at resolution, and that now threatens to force a fundamental revision of our cosmological model. The crisis has a name. It is called the Hubble tension, and it gets worse than anyone expected. Here is a number that should be simple. It should be one of the most straightforward measurements in all of cosmology. And instead, it has become one of the most dangerous. The number is the Hubble constant, designated by the symbol h0. It tells you how fast the universe is expanding, specifically, how much faster a galaxy is receding from us for every additional megaparsec of distance between us and it. 1 megaparsec is roughly 3.26 million light-years. The Hubble constant is expressed in units of kilometers per second per megaparsec, and in principle, measuring it is elegant in its simplicity. Find objects at known distances, measure their recession speeds via redshift, and divide speed by distance. The slope of that line gives you h0, simple, clean, foundational, and for the past decade, two of the most precise measurements of this single number have disagreed with each other so severely that the discrepancy now exceeds 5 standard deviations. The threshold physicists use to declare a genuine discovery. In particle physics, a 5 sigma result is considered proof that something real has been observed. Here, 5 sigma is telling us that something is wrong. One method says the universe is expanding at one rate. The other says it is expanding at a noticeably different rate. They cannot both be correct, and the implications of the disagreement are enormous, because this is not a minor cosmological detail. The Hubble constant sets the scale of the entire cosmos. It determines how old the universe is. It determines how large the observable universe is. It determines the balance between dark energy and matter. Getting H0 wrong means getting everything wrong. So what are these two measurements, and why do they refuse to agree? The first measurement comes from the cosmic microwave background, the faint, uniform glow of microwave radiation that fills all of space, interpreted by the standard cosmological model as the afterglow of the earliest epoch of the observable universe. The European Space Agency's Planck satellite spent 4 years mapping this radiation with extraordinary precision, measuring temperature variations as small as a few millionths of a degree. From those maps, physicists extracted a detailed picture of the universe's properties at a time roughly 380,000 years after the initial expansion of space began, according to the Lambda CDM model. Using those properties, the density of ordinary matter, the density of dark matter, the density of dark energy, the geometry of space, they calculated forward in time, using the equations of general relativity and the known physics of the expanding cosmos, to predict what the Hubble constant should be today. The answer, 67.4 kilometers per second per megaparsec, with an uncertainty of plus or minus 0.5. This measurement has been cross-checked by independent observations from the Atacama Cosmology Telescope, the South Pole Telescope, and the Wilkinson Microwave Anisotropy Probe. All agree. The early universe measurement is solid. The second measurement comes from the local distance ladder, and this is where variable stars take center stage. The Cepheids collaboration, whose name stands for supernovae and H0 for the equation of state, is led by Adam Riess, one of the 3 physicists who shared the 1998 Nobel Prize for the discovery that the expansion of the universe is accelerating. For more than 15 years, the Cepheids team has been refining the local measurement of H0 with a methodology built on 3 rungs. The first rung anchors the distance scale using geometric methods that do not rely on any assumptions about stellar physics. These include parallaxes of Milky Way Cepheids measured by the Gaia spacecraft, the distance to the Large Magellanic Cloud determined to about 1% precision using detached eclipsing binary systems, pairs of stars whose orbital geometry gives a direct distance, and the distance to the galaxy NGC 4258 measured using water masers, clouds of gas orbiting the galaxy's central black hole that emit microwave radiation whose Doppler shifts reveal the orbital velocities, which, combined with the angular size of the orbit, give a precise geometric distance. The second rung uses these anchored geometric distances to calibrate the period-luminosity relation for Cepheid variable stars. If you know the distance to a Cepheid, and you measure its period and apparent brightness, you can determine its absolute luminosity. Do this for dozens of Cepheids in the anchor galaxies, and you have a calibrated Leavitt law. Then, using the Hubble Space Telescope, you observe Cepheids in galaxies that also host Type Ia supernovae, thermonuclear explosions of white dwarf stars that produce a nearly uniform peak luminosity and thus serve as even brighter, standard candles. The third rung uses those calibrated Type Ia supernovae to reach into the deep universe, out to hundreds of megaparsecs, where Hubble's law can be measured directly, free of local gravitational effects. The recession velocities of galaxies at these distances give H0 cleanly. The result from the Cepheids team, using their most recent data including Hubble Space Telescope photometry and updated calibrations, 73.17 kilometers per second per megaparsec, with an uncertainty of plus or minus 0.86. The tension with the Planck early universe value now stands at 5.8 sigma. Let that sink in. The universe, as measured from its earliest light, is expanding at 67.4. The universe, as measured from pulsating stars and exploding white dwarfs in the local cosmos, is expanding at 73.2. The gap is roughly 6 kilometers per second per megaparsec. That sounds modest, but it is not. It translates into a difference of approximately 1 billion years in the estimated age of the universe. It changes the projected size of the observable cosmos. It alters the inferred density of dark energy, and it refuses to go away no matter how many times the measurements are repeated, refined, and cross-checked. Something is wrong with our assumptions. Either there is a systematic error hiding somewhere in one of the measurements, perhaps in how Cepheids are calibrated, or in how the cosmic microwave background data is interpreted, or the standard lambda CDM model of cosmology is missing something fundamental. A new particle, a new force, a new form of energy, a hidden epoch of physics between the early universe and today that changes the expansion rate in a way the model does not capture. Either possibility is profoundly unsettling, and the Cepheids sit right at the center of it. So the question becomes immediate and urgent. Could the problem be with the Cepheids themselves? Could the period luminosity relation that Henrietta Leavitt discovered more than a century ago contain a hidden systematic bias, an error that corrupts the entire distance ladder from the ground up? This is not a hypothetical concern. It is the subject of active, intense, sometimes contentious research. And the deeper you look, the more complex the picture becomes. The first complication is that there is not one type of Cepheid. There are two fundamentally different populations. Classical Cepheids, also called Type I Cepheids, are young, massive, metal-rich stars, typically 5 to 20 times the mass of the Sun, found in the disks of spiral galaxies in regions of active star formation. Their periods range from about 1 day to over 100 days, with luminosities thousands to tens of thousands of times that of the Sun. Type II Cepheids, including the W Virginis and BL Hercules subclasses, are older, lower-mass stars, roughly 0.5 to 0.8 solar masses, found in globular clusters and galactic halos. Type II Cepheids are intrinsically dimmer than classical Cepheids at the same period. So confusing the two types leads to systematic distance errors. This confusion plagued astronomy for 3 decades. When Edwin Hubble measured the distance to Andromeda in the 1920s, he used a calibration based on Cepheids in globular clusters, population II objects. He did not know he was comparing dim old stars to bright young ones. The result was that Andromeda appeared closer than it actually was, and the Hubble constant came out absurdly high, around 500 kilometers per second per megaparsec, implying a universe younger than the oldest known stars. This embarrassing contradiction persisted until Walter Beatty, in 1952, publicly announced at the International Astronomical Union meeting in Rome that the distance scale needed to be roughly doubled, because two types of Cepheids had been mixed together. Overnight, the universe became twice as large and approximately twice as old. The relief was enormous. The lesson was sobering. A fundamental error in the Cepheid calibration had misled the entire field for a generation. Could a similar error exist today? Modern astronomers are acutely aware of the danger. The SHU's calibration uses only classical Cepheids, carefully selected and vetted, but subtler issues remain. The period luminosity relation is not perfectly universal. It depends on the metallicity of the star, the abundance of elements heavier than helium in the stellar atmosphere. Cepheids in metal-rich environments may be slightly brighter or dimmer at the same period compared to Cepheids in metal-poor environments. And the magnitude and even the sign of this metallicity correction depends on the photometric band being used. In the near-infrared, the metallicity effect appears to be small. In the optical, it can be more significant. The Cepheid team applies metallicity corrections based on spectroscopic measurements of the Cepheids themselves, but the corrections carry their own uncertainties. A 2025 study by Hugos and Merzel from Stockholm University explored another possibility, that the period luminosity relation is not a single straight line at all, but may have different slopes in different period ranges, a broken or non-linear relation. Using the Cepheid data, they found that allowing the slope to change with period reduced the Hubble tension from 5.4 sigma to 4.4 sigma and shifted h0 down by about 1 kilometer per second per megaparsec. This is not enough to resolve the tension, but it demonstrates that the detailed shape of the period luminosity relation matters, and that assumptions about its linearity may carry consequences for the distance scale. Then there is the problem of photometric crowding. Many of the Cepheids observed by Cepheid are in distant galaxies, up to about 40 megaparsecs away, imaged with the Hubble Space Telescope's Wide Field Camera 3. At those distances, a single pixel on the detector can contain light from dozens of unresolved stars in addition to the Cepheid. This blending makes the Cepheid appear brighter than it truly is, which makes the host galaxy appear closer than it truly is, which biases H0 upward. The Cepheids team applies statistical corrections for this blending based on artificial star tests, injecting fake stars into the images and measuring how their photometry is affected by crowding. But these corrections are necessarily model-dependent, and independent groups have sometimes found different values. And it gets worse. There is interstellar extinction, the absorption and scattering of starlight by dust grains along the line of sight. Cepheids live in the dusty disks of spiral galaxies. Dust makes stars appear dimmer and redder, and correcting for it requires multi-wavelength observations to estimate the reddening. The standard assumption is that the dust properties follow a universal reddening law. The ratio of total to selective extinction is approximately 3.1. But this ratio can vary depending on the composition and size distribution of the dust grains. In some regions, it deviates significantly. If the reddening correction is wrong, the inferred luminosity of the Cepheid is wrong, and the distance is wrong. Then there are the anchor galaxies themselves. The Cepheid ladder rests on three primary geometric anchors: the Large Magellanic Cloud, NGC 4258, and Milky Way Cepheids with Gaia parallaxes. Each anchor contributes its own systematic uncertainties. The Large Magellanic Cloud distance, now known to about 1%, is anchored by 20 detached eclipsing binary systems measured by the Arcaria project over more than a decade. But even 1% uncertainty propagates multiplicatively through every subsequent rung of the ladder. The NGC 4258 distance relies on a Keplerian Maser-disk model that assumes the disk is flat, thin, and in purely circular orbits, assumptions that may not be perfectly met. And the Gaia parallaxes for nearby Cepheids carry systematic zero-point offsets that have been revised with each successive data release, though the most recent calibrations appear robust. Here is where the story takes an unsettling turn. Despite all of these potential systematics, multiple independent groups using different data, different analysis methods, and different standard candles have converged on a high value of H0 that is inconsistent with the Planck early universe prediction. The Chicago Carnegie Hubble program, using the tip of the red giant branch as an alternative distance indicator, initially reported a value around 69.8, lower than shows but still above Planck. Subsequent recalibrations have pushed this result toward the Cepheid range. The Megamaser Cosmology project, using geometric distances to galaxies hosting water masers, finds H0 around 73. The HOLYCO project, using time delays in gravitationally lensed quasars, a method completely independent of any stellar distance indicator, reported 73.3. These independent lines of evidence all point in the same direction. And in 2024, the James Webb Space Telescope delivered what many hoped would be the decisive test. JWST observed Cepheids in several Cepheid galaxies with its near-infrared camera, which has far superior resolution compared to the Hubble Space Telescope. The concern was that Hubble's crowding corrections might be systematically flawed, that unresolved stellar blending could have corrupted the Cepheid photometry and artificially inflated H0. But JWST, with its sharper eye, confirmed the Hubble photometry. The Cepheid brightnesses measured by the two telescopes agreed. The crowding correction was not the culprit. The Hubble tension, as it is now universally called, appears to be real. It is not a measurement error. It is not a calibration mistake. It is a genuine disagreement between the early universe and the local universe about how fast the cosmos is expanding, and the implications are staggering. If the tension is genuine, if no systematic error is hiding in either measurement, then the lambda CDM model of cosmology is incomplete. The most successful predictive model in the history of physics, one that has passed dozens of independent observational tests over 2 decades, is missing something. The expansion history of the universe does not follow the trajectory that lambda CDM predicts. Somewhere between the epoch of the cosmic microwave background and the present day, something happened that the model does not account for. What could it be? The proposals are numerous and often exotic. Early dark energy, a temporary burst of vacuum energy in the first 100,000 years or so, which would have changed the size of the sound horizon, the characteristic scale imprinted in the cosmic microwave background. This would alter the Planck inference of h0 without changing the local measurement. Proposals involving extra-relativistic species, additional neutrino-like particles that increase the radiation density in the early universe and change its expansion rate, modified gravity theories that alter the relationship between matter and geometry, decaying dark matter models where a fraction of the dark matter converts to radiation at some intermediate epoch, interactions between dark energy and dark matter that change the late-time expansion history. The situation has been called the Hubble Olympics, a competition among theoretical models to explain the discrepancy. So far, no clear winner has emerged. Many models that fix the Hubble tension create new tensions with other datasets: baryon acoustic oscillations, galaxy clustering, weak gravitational lensing. The problem is not a lack of ideas. It is a lack of ideas that work. And at the heart of it all, the pulsating stars, the Cepheids that breathe in and out, the Ara Lyrae variables that pulse in globular clusters, the Type Ia supernovae calibrated by Cepheid distances. The entire local measurement of the Hubble constant rests on a chain of standard candles, whose first link was forged by Henrietta Leavitt in a basement in Cambridge, Massachusetts, more than a century ago. If the Cepheids are pointing us toward new physics, then pulsating stars will have done something even more extraordinary than measuring the size of the universe. They will have revealed that our model of the universe itself is broken. To appreciate the full weight of this crisis, consider the history of the Hubble constant. The original value measured by Edwin Hubble himself in 1929 was approximately 500 kilometers per second per megaparsec, a number that implied a universe younger than the Earth, an obvious absurdity that took decades to resolve. Beatty's correction in 1952 brought it down to about 250. Subsequent work by Alan Sandage, using improved Cepheid photometry and better extinction corrections, pushed it below 100 by the 1970s. For decades, the community was split into two camps. Sandage and his collaborators favoured a value around 50, while Gérard de Vaucouleurs and others preferred a value around 100. The disagreement was bitter, personal, and seemingly irresolvable. The resolution came from the Hubble Space Telescope itself. One of the key scientific justifications for building and launching the telescope was the precise determination of h0. A dedicated program, the Hubble Space Telescope Key project on the extragalactic distance scale, used Cepheid observations in 18 galaxies to calibrate several secondary distance indicators and converged on a value of 72 kilometers per second per megaparsec, plus or minus 8, published in 2001. This narrowed the range dramatically and appeared to settle the debate. The old war between 50 and 100 was over. The answer was in the 70s. But then the Planck satellite weighed in, and the new war began. What makes the current tension so much more troubling than the old Sandage-de Vaucouleurs disagreement is the precision. In the old days, the uncertainties were 20% or more, and the two values overlapped within their error bars. Today, the uncertainties are at the 1 to 2% level, and the values do not overlap. The Planck result of 67.4 and the Cepheid result of 73.2 are separated by 8%, which, given the tiny error bars, corresponds to a statistical significance exceeding 5 sigma. In the language of physics, this is either a systematic error of improbable magnitude or a genuine discrepancy requiring new physics. The James Webb Space Telescope results from 2024 deserve particular attention. The concern was specific and well-defined, that the Hubble Space Telescope, with its relatively broad point spread function in the infrared, might be systematically overestimating the brightness of Cepheids in crowded star fields. JWST, with a primary mirror 6.5 meters across compared to Hubble's 2.4, has dramatically sharper resolution in the near-infrared. The Cepheid team targeted several galaxies where Cepheids had been previously measured with Hubble and observed them with JWST's near-infrared camera. The result was unambiguous. The Cepheid magnitudes agreed between the two telescopes to within the measurement uncertainties. The crowding bias, which had been the most widely cited potential systematic, was confirmed to be correctly accounted for in the Shuiz analysis. Adam Rias remarked that this result effectively closed one of the most important escape hatches for those hoping to resolve the tension through measurement error. Other independent distance measurements reinforce the high-value camp. The Megamaser Cosmology project measures geometric distances to galaxies hosting water maser disks around their central black holes. The technique is entirely independent of any stellar physics. No Cepheids, no tip of the red giant branch, no Type Ia supernovae are involved. Their result: approximately 73.9 kilometers per second per megaparsec, consistent with Shuiz. The Holocaust collaboration, now part of the broader TD Cosmo program, uses gravitationally lensed quasars to measure H0. When a distant quasar's light passes near a massive galaxy, the galaxy's gravity bends the light along multiple paths, creating multiple images. Because each path has a slightly different length, variations in the quasar's brightness arrive at Earth at slightly different times. These time delays, combined with a model of the lensing galaxy's mass distribution, give a geometric distance measurement and hence H0. The result: 73.3, with an uncertainty of about 1.7, fully consistent with the local distance ladder. Surface brightness fluctuations, a technique that measures the pixel-to-pixel variance in galaxy images, which depends on the distance, give yet another independent high value. Gravitational wave observations of neutron star mergers, which can yield luminosity distances independently of any electromagnetic calibration, are beginning to constrain H0 as well, though current uncertainties are still too large to be decisive. The weight of evidence is accumulating. Multiple methods using different physics, different telescopes, and different analysis pipelines converge on a local value of H0 around 72 to 74. Multiple early universe methods converge on a value around 67 to 68. The gap is persistent, robust, and deeply consequential. On the theoretical side, the most actively investigated proposal is early dark energy, a scalar field that contributes a small fraction of the total energy density in the early universe at redshifts of a few thousand, and then decays away rapidly. This would reduce the sound horizon. The characteristic scale, imprinted in the cosmic microwave background by acoustic oscillations in the primordial plasma, which in turn would cause the Planck analysis to infer a higher value of H0, potentially closing the gap. The early dark energy model proposed by Poulin, Smith, Karwal, and Kamionkowski in 2019 garnered significant attention, but subsequent studies have shown that it creates mild tensions with other datasets, including baryon acoustic oscillation measurements and the full-shape power spectrum of galaxy clustering. Other proposals include extra-sterile neutrinos that increase the radiation density in the early universe, interacting dark energy models where dark energy couples to dark matter and alters the late-time expansion history, and modifications to general relativity itself. A comprehensive review published in 2021 by Di Valentino and colleagues catalogued more than 1,000 papers proposing solutions to the Hubble tension. None has achieved consensus. The problem remains wide open, but the Hubble tension is not the only revelation that variable stars are delivering. Because while Cepheids have been rewriting cosmology, an entirely different frontier of pulsation science has been rewriting our understanding of stellar interiors. Stars do not just pulse at a single frequency. Many of them vibrate in complex patterns, multiple modes simultaneously, like a cathedral organ playing several notes at once. And the pattern of those vibrations encodes information so deep that no telescope, no matter how powerful, could ever access it by any other means. This is the science of asteroseismology, and some of the answers it has provided do not match the predictions. The interiors of stars, as revealed by their oscillations, are not arranged the way our models say they should be. The rotation rates are wrong. The mixing is different. The core structures are unexpected. We thought we understood stars. The pulsations are telling us we were overconfident. And the more closely we listen, the more surprises emerge. The Ara Lyrae stars, the smaller, older, less luminous cousins of the Cepheids, have their own constellations of unsolved mysteries that deepen the picture. These are truly ancient stars, among the oldest in the Milky Way, with ages estimated at 10 to 12 billion years according to current stellar models. They have masses of roughly 0.6 to 0.7 times the mass of the Sun. They have lived extraordinary lives, burning through their core hydrogen over billions of years, ascending the red giant branch as their envelopes expanded, reaching the tip of the red giant branch where helium in the core ignited in a violent runaway thermonuclear event called the helium flash, and then settling onto the horizontal branch where they now burn helium steadily in their cores, surrounded by a shell of hydrogen fusion. Those that land within the instability strip during this horizontal branch phase become RR Lyrae variables. Their pulsation periods are short, between about 0.2 and 1 day, and their luminosities are remarkably uniform. Almost all RR Lyrae stars have an absolute visual magnitude of about plus 0.75, corresponding to roughly 50 times the luminosity of the Sun. This near uniformity makes them excellent standard candles, particularly for measuring distances within the Milky Way and to nearby dwarf galaxies and globular clusters. You do not even need to know the period precisely. Just identifying a star as an RR Lyrae immediately gives you an approximate luminosity, and from the apparent brightness, you can estimate the distance. But the RR Lyrae stars carry a secret that has confounded astronomers for more than a century. Many of them, estimates range from roughly 40 to 50%, exhibit a puzzling slow modulation of their pulsation amplitude and phase. This is called the Blaschko effect, named after the Russian astronomer Sergei Nikolaevich Blaschko, who first identified it in 1907 when he noticed that the star RW Draconis showed periodic changes in the shape and height of its maximum brightness, superimposed on the faster primary pulsation. The Blaschko effect manifests as a slow, periodic rise and fall in the pulsation amplitude, along with a shift in the timing of maximum light, over timescales ranging from roughly 10 days to several hundred days. In some stars, the modulation is dramatic. The maximum brightness varies by half a magnitude or more from one Blaschko cycle to the next. In others, it is subtle, detectable only with precise photometry. Despite more than a century of effort, no single theoretical model fully explains the Blaschko effect. Several competing hypotheses have been proposed, each with strengths and weaknesses. The resonance model suggests that the Blaschko effect arises from a nonlinear interaction between the fundamental radial pulsation mode of the star and a nearby non-radial mode. If two modes have frequencies that are nearly, but not exactly, commensurate, they can beat against each other, producing the slow amplitude modulation. This model can reproduce some features of the Blaschko effect, but it struggles to explain why the modulation period is so different from the pulsation period, and it requires the existence of specific non-radial modes that are not always observed. The magnetic model proposes that a magnetic field tilted relative to the star's rotation axis creates an asymmetric pulsation, stronger on one side of the star than the other. As the star rotates, the asymmetry sweeps around, modulating the observed amplitude and phase. This would tie the Blaschko period to the rotation period. The model is elegant, but direct measurements of magnetic fields in RR Lyrae stars have yielded conflicting results, with some studies detecting weak fields and others finding none at all. The convective quenching model suggests that turbulent convection in the star's outer layers interacts with the pulsation in a time-variable way, alternately enhancing and suppressing it. This is perhaps the most physically realistic model, but also the most computationally difficult to test, because three-dimensional radiation hydrodynamic simulations of convection in pulsating stars are at the frontier of computational astrophysics. And then the Kepler Space Telescope made everything more complicated. When Kepler observed RR Lyrae stars with photometric precision of a few parts per million, hundreds of times better than anything achievable from the ground, it revealed fine structure in the Blaschko modulation that no one had anticipated. Additional pulsation frequencies appeared in the Fourier spectra, including frequencies at half-integer multiples of the fundamental mode, a phenomenon known as period doubling. In period doubling, the star alternates between higher and lower brightness maxima on successive pulsation cycles so that the effective period appears to double. This had been predicted theoretically for strongly nonlinear pulsation models, but had never been convincingly observed before Kepler. The discovery of period doubling in RR Lyrae stars demonstrated that these oscillations are deeply nonlinear. The pulsation amplitude is large enough that the linear approximation used in most theoretical models breaks down. Understanding the Blaschko effect will ultimately require fully nonlinear, three-dimensional hydrodynamic simulations that include radiation transport, convection, and possibly magnetic fields. These simulations are beginning to appear, but they are enormously expensive computationally, and the field is still far from a definitive explanation. Here is something that deepens the puzzle further. Not all RR Lyrae stars show the Blaschko effect. Some are remarkably stable, pulsating at constant amplitude for decades. What determines whether a given RR Lyrae star will exhibit the Blaschko modulation? The answer is not known. Statistical studies show that Blaschko stars tend to have slightly different physical properties, different metallicities, different pulsation amplitudes than non-Blaschko stars, but the overlap is large. There is no clear dividing line. This means that the Blaschko effect is not simply a consequence of being in a particular part of the instability strip. Something else, some property of the star's internal structure, its rotation or its magnetic field, determines whether the modulation appears or not. Identifying that property would likely solve the entire mystery. The Kepler data also revealed an even more exotic phenomenon: additional frequencies in RR Lyrae stars that do not correspond to any expected radial or non-radial oscillation mode. These extra frequencies, sometimes appearing in the Fourier spectrum at specific fractions of the fundamental mode frequency, have no established theoretical explanation. They may arise from strange mode oscillations, a class of pulsation modes that occur in stars with very extended low-density envelopes where the usual classification of modes breaks down, or they may reflect nonlinear coupling between modes in ways that current models do not capture. Their mere existence is a challenge to our understanding of stellar oscillation theory. The Blaschko effect matters for more than theoretical tidiness. RR Lyrae stars are used as distance indicators throughout the Milky Way and beyond, and the Blaschko modulation directly affects the mean brightness of the star. If the average magnitude over a Blaschko cycle differs from the average over a single pulsar cycle, then an observer who measures the star at a random time will get a biased distance estimate. Studies have shown that the mean brightness of Blaschko RR Lyrae stars varies by up to 0.1 magnitude over the modulation cycle, corresponding to distance errors of roughly 5%. For an individual star, 5% may seem tolerable, but when you are using RR Lyrae stars to map the three-dimensional structure of the Milky Way's halo, to determine the distance to globular clusters with percent-level accuracy, or to calibrate other rungs of the distance ladder, even small systematic biases accumulate and compound. This is a recurring theme in the study of variable stars. The physics that makes them useful as distance indicators, their regular pulsation, their predictable brightness, is entangled with the physics that makes them complicated. Nonlinear dynamics, convection, mass loss, magnetic fields, and binary companions. Every attempt to sharpen the distance measurements eventually runs into a deeper layer of stellar physics that must be understood first. The tool and the science are inseparable, and this entanglement has consequences that reach far beyond the measurement of distances. Because if our models of stellar pulsation are incomplete, if the interiors of stars are structured differently from what we calculate, if the mixing of elements is different, if the rotation profiles are wrong, then every prediction that depends on those models is also at risk. Stellar ages calculated from evolutionary models could be off. Chemical abundance patterns inferred from spectral analysis could be misleading. Even our understanding of how galaxies evolve over cosmic time depends on getting the details of stellar physics right, because stars are the engines that drive galactic evolution, through their radiation, their winds, their explosions, and their deaths. Variable stars are not just markers on a cosmic map. They are the testing ground where our theories of stellar structure and evolution are either confirmed or broken. And in the 21st century, Thanks to space telescopes that can detect stellar oscillations with parts per million precision, the testing has become more rigorous than ever before. The results, as we will see, are simultaneously thrilling and humbling. RR Lyrae stars are used as distance indicators, and the Blasco modulation affects their mean brightness. If the mean magnitude changes over the Blasco cycle, then a snapshot observation made at the wrong phase could give a biased distance. Understanding the Blasco effect is therefore directly relevant to the accuracy of the RR Lyrae distance scale, and through it, to our mapping of the Milky Way and the local group. But the mysteries of variable stars extend beyond the instability strip altogether. Far off in the cool, red corner of the Hertzsprung-Russell diagram, on the asymptotic giant branch, lives another population of pulsators whose behavior carries profound implications for stellar evolution, for the chemical enrichment of the cosmos, and for the very atoms that make up your body. These are the Mira variables, and their story is one of beauty, violence, and the slow mechanics of stellar death. Mira variables are named after the prototype star Mira, also known by its catalogue designation Omicron Ceti, in the constellation Cetus the Whale. The name means the wonderful in Latin, given by the Polish astronomer Johannes Hevelius in 1662. The star's variability had been noticed even earlier. The German astronomer David Fabricius first recorded it as a new star in 1596, only to see it from visibility months later and then return. The repeated disappearances and reappearances baffled astronomers for decades. We now know that Mira varies in visual brightness by roughly 8 magnitudes over a period of about 332 days, meaning it swings between roughly 1,500 times the luminosity of the Sun in visible light at its brightest and nearly invisible to the naked eye at its faintest. Mira variables are red giants on the asymptotic giant branch, stars that have exhausted both hydrogen and helium in their cores, and are now powered by nuclear burning in thin shells surrounding an inert carbon-oxygen core. Their outer envelopes are enormously distended, swollen to radii of roughly 200 to 400 times that of the Sun. If you placed a typical Mira at the center of the solar system, its surface would reach roughly the orbit of Mars, possibly further. The entire star pulsates, expanding and contracting radially with periods ranging from about 100 to 1,000 days, and visual amplitude changes of more than 2.5 magnitudes. The defining characteristic that separates Miras from their less dramatic cousins, the semi-regular variables. The pulsation of Mira variables generates powerful shock waves that propagate outward through the stellar atmosphere. These shocks are critically important because they levitate gas to distances far above the photosphere, creating an extended region where temperatures drop low enough, roughly 1,000 to 1,500 degrees Kelvin, for microscopic dust grains to condense out of the gas. Once formed, these dust grains absorb and scatter the starlight pouring outward from the photosphere. The radiation pressure on the dust grains pushes them away from the star. The dust drags the surrounding gas along through collisions, creating a sustained stellar wind, a river of matter flowing outward from the star into interstellar space. Mass loss rates from Mira variables range from roughly 10 to the -8 to 10 to the -5 solar masses per year. At the upper end, a Mira can lose an entire sun's worth of mass every 100,000 years. Over the millions of years that a star spends on the asymptotic giant branch, this wind strips away the entire hydrogen-rich envelope, eventually exposing the hot, dense carbon-oxygen core. That core, no longer hidden beneath a bloated atmosphere, ionizes the surrounding expelled gas with its ultraviolet radiation, creating a glowing shell that we observe as a planetary nebula. The core itself cools and contracts to become a white dwarf, a stellar remnant roughly the size of the Earth, but with a mass comparable to the Sun's. The pulsation of a Mira variable is therefore not merely a periodic light variation. It is the engine of stellar death. Each pulsation cycle generates a shock. Each shock lifts gas. The gas forms dust. The dust catches starlight. And the star slowly, steadily bleeds itself into space, cycle by cycle, millennium by millennium, until only its core remains. And this process has consequences far beyond the star itself. the material expelled by Mira variables and other asymptotic giant branch stars is enriched with heavy elements, carbon, nitrogen, oxygen, silicon, and dozens of others, that were synthesized in the star's interior and carried to the surface by a deep mixing process called the third dredge-up. During the third dredge-up, the convective envelope of the star penetrates deep enough to reach layers where helium burning has produced carbon and other elements, and carries this newly forged material to the surface. In oxygen-rich Miras, those where the ratio of oxygen to carbon in the atmosphere exceeds 1, the stellar wind creates silicate dust, the same mineral family that makes up most of Earth's crust and mantle. In carbon-rich Miras, those where carbon exceeds oxygen, typically after several episodes of dredge-up, the wind creates carbonaceous dust and molecules like silicon carbide. These different dust species absorb and emit radiation at different wavelengths, giving oxygen-rich and carbon-rich Miras dramatically different infrared signatures. The contribution of asymptotic giant branch stars to the chemical evolution of galaxies is enormous. Scientific estimates suggest that they are responsible for roughly half of all elements heavier than iron in the universe, produced through a process called the slow neutron capture process, or S process, where atomic nuclei gradually absorb neutrons over thousands of years and build up heavier elements step by step. The S process produces elements like barium, strontium, lead, and many of the rare Earth elements. Without the pulsation-driven winds of Miras and their kin, these elements would remain locked in stellar interiors, unavailable for incorporation into new stars, planets, and ultimately living organisms. In a very real sense, the rhythm of Mira pulsation echoes in the periodic table itself. In 2007, NASA's Galaxy Evolution Explorer ultraviolet telescope made a stunning discovery about the prototype star Mira itself. It revealed that Mira is shedding material at such a prodigious rate and moving through space at such a high velocity, roughly 130 kilometers per second, relative to the surrounding gas, that it has left behind an enormous trail of material stretching 13 light-years through space. This tail, visible only in ultraviolet light, traces Mira's path through the galaxy over the past 30,000 years, and contains enough mass to form roughly 3,000 Earth-mass planets. It is a comet-like wake on a stellar scale, and it was created by the pulsation-driven mass loss of a single variable star. The Miras remind us, in the most visceral way, that stellar pulsation is not an abstract phenomenon studied in textbooks. It is a force that shapes galaxies, enriches the cosmos with the elements of life, and ultimately determines the fate of stars. The breathing of a Mira is its dying, and in that dying, new possibilities are born. But here is what makes this truly terrifying. The mass loss rates of Mira variables and the dust formation that drives their winds are not well constrained by current models. The relationship between pulsation amplitude, mass loss rate, and dust production involves deeply nonlinear, three-dimensional physics, convection, radiation hydrodynamics, grain nucleation and growth, molecular chemistry, that is extraordinarily difficult to simulate from first principles. Current models can reproduce the general features of Mira pulsation and mass loss, but they disagree on details. Different codes give different mass loss rates for the same stellar parameters. Different prescriptions for dust opacity give different wind velocities. The uncertainty in Mira mass loss rates translates directly into uncertainty in how much material these stars return to the interstellar medium, how quickly they evolve to the white dwarf stage, and how the chemical evolution of galaxies proceeds. The pulsation of variable stars, in every form, from the clockwork regularity of Cepheids to the chaotic nonlinearity of Miras, continues to reveal both extraordinary power and uncomfortable gaps in our understanding. And the family of pulsating variables is larger and more diverse than even these major categories suggest. Semi-regular variables, red giants and supergiants that show periodicity, but with less regularity and smaller amplitude than Miras, occupy a transitional zone between the well-behaved and the chaotic. Some semi-regular variables pulsate in overtone modes rather than the fundamental mode, producing shorter periods at the same luminosity. Recent large-scale surveys, including the OGLE project monitoring millions of stars in the Magellanic Cloud as the galactic bulge, have revealed that red giant pulsators, lie on at least 5 distinct period luminosity sequences, corresponding to pulsation in different radial modes. The fundamental first overtone, second overtone, third overtone, and a mysterious sequence whose physical origin is still debated. The identification of these sequences required the statistical power of monitoring hundreds of thousands of red giants simultaneously, and it has provided a new framework for understanding how pulsation modes evolve as a star ascends the giant branch. Among the most dramatic semi-regular variables are the red supergiants, stars like Betelgeuse in Orion, which made international headlines in late 2019 and early 2020 when it underwent an unprecedented dimming event, dropping to roughly 60% of its normal brightness. The Great Dimming of Betelgeuse, as it came to be called, initially sparked speculation that the star might be about to explode as a supernova. The truth turned out to be more subtle but no less fascinating. A combination of a pulsation-driven cooling event and the ejection of a large cloud of dust from the star's surface, the dust condensing in a plume of gas expelled by the star's convective activity, and pulsation conspired to block a significant fraction of the star's light as seen from Earth. The event demonstrated vividly how pulsation and convection in red supergiants work together to produce dramatic, rapid changes in brightness, and it highlighted how much we still have to learn about the outermost layers of these enormous, turbulent stars. The stars are speaking clearly. We are still learning the language, and the story is about to take its most dramatic turn yet, because the 20th century gave us the Cepheid distance ladder and the measurement of cosmic expansion. The 21st century has given us something even more powerful, the ability to see inside stars, not with X-rays, not with neutrino detectors, but with pulsations themselves. By recording the precise frequencies at which a star vibrates and comparing those frequencies to theoretical models of stellar structure, astronomers can reconstruct the density, temperature, composition and rotation of the stellar interior with astonishing detail. The technique is called asteroseismology, and it has been enabled by space telescopes of extraordinary photometric precision. The results have been transformative. They have revealed that the cores of red giant stars rotate far more slowly than predicted. They have shown that the internal mixing of elements in massive stars is more vigorous than models assume. They have uncovered discrepancies in the structure of the Sun itself, the one star that should, by all rights, be the best understood, and they have demonstrated conclusively that our models of stellar interiors need fundamental revision. The pulsation of variable stars is no longer just a distance measurement tool. It is a window into the deepest, most inaccessible regions of stellar matter, a stethoscope pressed against the heart of a star. And what that stethoscope is revealing will reshape astrophysics for decades to come. The history of understanding variable stars is not a single straight line from ignorance to knowledge. It is a series of brilliant attempts, spectacular failures, unexpected revelations, and hard-won insights, each one peeling back another layer of a mystery that turned out to be deeper and stranger than anyone imagined. What follows are the key chapters of that unfolding story. The missions, the theories, the individuals, and the moments that transformed our understanding of why stars pulse and what those pulses can tell us about the cosmos. Chapter 1. Arthur Eddington and the Dream of a Stellar Heat Engine. In the early 1920s, British astrophysicist Arthur Stanley Eddington was, by any measure, one of the most formidable scientific minds on the planet. He had led the 1919 solar eclipse expedition that confirmed Einstein's general theory of relativity by measuring the bending of starlight near the Sun, a result that made Einstein a global celebrity. He had pioneered the theoretical understanding of stellar interiors, demonstrating that stars are gaseous throughout, and that radiation pressure plays a crucial role in supporting them against gravitational collapse. He had developed the mass-luminosity relation, showing that a star's luminosity depends primarily on its mass. And now, in the mid-1920s, he turned his formidable intellect to a question that had puzzled astronomers for decades. Why do Cepheid variables pulsate? At the time, the dominant hypothesis was that Cepheids were binary star systems, that the periodic brightness changes were caused by orbital eclipses. But this idea had a fatal flaw that careful observers had already identified. The light curves of Cepheids were asymmetric. The rise to maximum brightness was rapid, while the decline was slow, producing a distinctive sawtooth pattern. Binary eclipses produce symmetric dips. A star moves in front, blocks the light, then moves away. They do not produce sawtooth waves. Moreover, spectroscopic observations using the Doppler effect showed that the surface of a Cepheid was physically moving, approaching and receding periodically in sync with the brightness variations. The star was not being eclipsed, it was physically expanding and contracting. Eddington proposed in his landmark 1926 book, The Internal Constitution of the Stars, that the pulsation was maintained by a valve-like mechanism, a thermodynamic engine operating within the star's interior. He imagined a layer that would trap heat when compressed and release it when expanded, converting thermal energy into mechanical oscillation. He called this a stellar heat engine, drawing an explicit analogy to the pistons and valves of a steam engine. The idea was brilliant and conceptually correct, but Eddington could not identify the specific layer responsible for the valve effect. The detailed physics of stellar opacities, how different elements absorb and scatter radiation at different temperatures and densities, was not yet sufficiently understood. The problem lingered for nearly 3 decades. Astronomers knew that pulsation was real. They knew it was radial, the whole star expanding and contracting like a breathing sphere, but they could not explain why the oscillation was self-sustaining rather than damping away. In most stellar material, compression increases the temperature, which decreases the opacity, which allows energy to escape more easily, which reduces the pressure, which damps the oscillation. The star should stabilize. Why doesn't it? The answer came from an unexpected direction. In the late 1950s, the Soviet physicist Sergei Alexandrovich Zhevakin published a series of papers identifying the second helium ionization zone as the driver of Cepheid pulsation. Independently, John Cox and his colleague Charles Whitney at the Los Alamos National Laboratory, a facility better known for nuclear weapons research, were developing their own detailed models of stellar pulsation. By 1963, Cox had published a comprehensive treatment of the Kappa mechanism, demonstrating conclusively that the partial ionization of helium created exactly the kind of opacity valve that Eddington had envisioned. When helium is partially ionized, compression drives further ionization rather than temperature increase. The opacity rises, energy is trapped, pressure builds, the layer is pushed outward. Expansion reverses the process, and the cycle repeats. Eddington had been vindicated 30 years after his death. His intuition about a stellar heat engine was correct in every essential respect. He had simply lacked the opacity calculations needed to identify the specific layer. The resolution of this problem remains one of the most elegant achievements in stellar astrophysics, a mechanism of beautiful simplicity, a partially ionized gas acting as a thermodynamic valve, explaining one of the most conspicuous phenomena in the night sky. It was a reminder that the right physical intuition, even when it cannot be fully justified in its own time, can illuminate the path for future generations of scientists who possess the tools to complete the argument. But the triumph of the Kappa mechanism also exposed the limits of our understanding. The mechanism explains why stars pulsate when they enter the instability strip, but it does not perfectly predict the boundaries of that strip. The blue edge, the hot boundary, is reproduced reasonably well by linear pulsation theory. The red edge, the cool boundary, is not, because at cooler temperatures, the outer layers of the star become convective, and convection and pulsation interact in deeply nonlinear ways that remain difficult to model even with modern supercomputers. Getting the red edge right requires time-dependent convection models that are still being developed and debated. This is not a minor issue. The red edge determines which cool stars pulsate and which do not, and therefore affects the population statistics of Cepheids and RR Lyrae stars used for distance measurements. The numbers are striking. The blue edge of the classical Cepheid instability strip sits at a surface temperature of roughly 7,500 Kelvin. The red edge sits at roughly 5,500 Kelvin. That is a window of about 2,000 degrees, remarkably narrow for stellar astrophysics, where temperatures span from roughly 3,000 Kelvin for the coolest red dwarfs to over 40,000 Kelvin for the hottest O-type stars. Within that narrow window, the entire phenomenon of Cepheid pulsation arises, along with all of the cosmological measurements that depend on it. If the strip were shifted by even a few hundred degrees, if the opacity physics were slightly different, if the helium abundance were different, the Cepheids might not pulsate at all, and humanity might never have discovered the expansion of the universe. Chapter 2. Walter Bahr and the Doubling of the Universe. In the autumn of 1942, the skies above Los Angeles went dark, not from a solar eclipse, but from wartime blackout regulations imposed after the Japanese attack on Pearl Harbor. For the general public, the blackouts were an anxious reminder of the war. For Walter Bahr, a German-born astronomer working at the Mount Wilson Observatory, they were an extraordinary gift. The 100-inch Hooker telescope, normally hampered by the light pollution of the growing city below, suddenly had access to some of the darkest skies it had ever enjoyed. Bahr seized the opportunity with characteristic thoroughness and ambition. He pointed the great telescope at the Andromeda galaxy, and, for the first time, resolved individual stars in its central bulge and in the globular clusters surrounding it. What he saw was striking and unexpected. The brightest stars in the bulge and in the globular clusters were red, not blue. This was the opposite of what he observed in the spiral arms, where the brightest stars were hot, young blue supergiants. Bahr was looking at two fundamentally different stellar populations, and he coined the terms that would define them. Population I for the young, metal-rich stars found in galactic disks, and Population II for the old, metal-poor stars found in halos, bulges, and globular clusters. This seemingly abstract classification had immediate, explosive consequences for the measurement of cosmic distances. Edwin Hubble's original distance to Andromeda, the measurement that proved it was a separate galaxy, had been calibrated using a period luminosity relation derived from Cepheids in globular clusters. But globular cluster Cepheids, Bahr now realized, belonged to Population II. They were intrinsically dimmer than the Population I classical Cepheids found in galactic disks. Hubble had been using the brightness of dim old stars as a yardstick for bright young ones. Every extragalactic distance he had ever measured was wrong, systematically underestimated. In 1952, at the International Astronomical Union meeting in Rome, Bahr announced his findings. The distance scale of the universe needed to be approximately doubled. Andromeda was not 900,000 light-years away, as Hubble had calculated. It was closer to 2 million light-years, a figure that has since been refined to about 2.5 million light-years with modern measurements. The Hubble constant plummeted from about 500 to about 250 kilometers per second per megaparsec. The universe was instantly twice as large and approximately twice as old. The embarrassing problem of stars appearing older than the universe was resolved in a single stroke. The reaction from the astronomical community was profound. Some were relieved. The old distance scale had produced paradoxes that everyone knew were untenable. Others were shaken. If such a fundamental error could persist for 3 decades, undetected despite the efforts of the world's best observers, what other errors might be lurking? Bahr's correction was not the result of a new telescope or a new technique. It was the result of recognizing a distinction, Population I versus Population II, that had been hiding in plain sight all along. But Bahr's correction was only the beginning of a long, painful process of refining the distance scale. Throughout the 1950s and 60s, Alan Sandage, Hubble's protégé and intellectual heir, worked tirelessly to recalibrate the distance ladder, finding additional errors at every rung. The brightest stars in distant galaxies that Hubble had mistaken for individual supergiants turned out to be compact clusters of stars, HI regions, and were therefore far more luminous than any single star. Correcting for this pushed the distance scale further outward and drove the Hubble constant lower still, from Bahr's revised estimate of roughly 250 down to values near 75 kilometers per second per megaparsec. The saga of Bahr's revision illustrates a principle that runs through the entire history of variable star astronomy. Nature's apparent simplicity conceals genuine complexity, and progress comes not from trusting the elegant relationship at face value, but from interrogating it with enough rigor to uncover the hidden systematics. The period luminosity relation for Cepheids remains one of the most powerful tools in observational cosmology, but every digit of the Hubble constant it delivers is earned through the painstaking work of understanding stellar populations, chemical compositions, and the physics of pulsation with ever-increasing precision. The lesson was permanent. The Cepheid distance ladder is only as good as our understanding of the stars that make it up. Mix up the stellar populations, misunderstand the metallicity effects, underestimate the extinction correction, and the entire structure tilts. The ladder is powerful, but it is also fragile, and its reliability depends on understanding the full complexity of stellar physics. Chapter 3. The Kepler Revolution and the Sound of Stars in March of 2009. A Delta II rocket lifted off from Cape Canaveral, carrying a spacecraft that would change the landscape of stellar astrophysics more profoundly than any instrument since the invention of the telescope. The Kepler Space Telescope was designed with a focused primary mission to detect Earth-sized planets orbiting Sun-like stars by monitoring the tiny dips in starlight caused by planetary transits. To achieve this, Kepler needed to stare at a single patch of sky, a field in the constellations Cygnus and Lyra, with photometric precision of a few parts per million, continuously, for years. Those capabilities, precision at the parts per million level, continuous coverage without atmospheric gaps, and a 4-year baseline made Kepler not just a planet hunter, but the most powerful astroseismology instrument ever built. The same sensitivity that let Kepler detect a planet dimming a star by 1/100% also let it detect the faint oscillation modes of stars, vibrating with amplitudes too small for any ground-based telescope to measure. And when astronomers turned the astroseismic analysis pipeline on Kepler's vast dataset, the results were revolutionary. Consider what happens inside a star like the Sun. Its outer layers are convective. Great cells of hot gas rise from the interior, cool at the surface, and sink back down. This churning convection generates acoustic noise, sound waves that propagate into the stellar interior. Some of these sound waves bounce off internal boundaries, reflect back to the surface, and interfere with each other, creating standing wave patterns called oscillation modes. These are pressure modes, or P modes, and the Sun has millions of them, each vibrating at a slightly different frequency, like the overtones of an enormously complex musical instrument. The frequencies of these modes depend on the star's internal structure, the sound speed profile, which in turn depends on the temperature, density, and chemical composition as a function of depth. By measuring the frequencies with precision and comparing them to theoretical models, astronomers can reconstruct the internal structure. This is exactly analogous to how a seismologist uses earthquake waves to map the Earth's interior. By tracking how the waves travel, what they reflect off of, and how fast they propagate, you build a picture of what lies beneath the surface. Helioseismology, the asteroseismology of the Sun, had been pursued from the ground since the 1970s, using instruments that measured tiny Doppler shifts in solar spectral lines caused by the surface oscillations. The results were spectacular. Helioseismologists determined the depth of the solar convection zone, about 200,000 kilometers below the surface, or roughly 30% of the way to the center, with a precision of better than 1%. They mapped the Sun's internal rotation as a function of both latitude and depth, discovering that the convection zone rotates differentially, faster at the equator, slower at the poles, while the radiative interior below rotates nearly uniformly. They measured the sound speed throughout the solar interior and found remarkable agreement with theoretical solar models, vindicating decades of work in stellar structure theory. But the agreement was not perfect. Small discrepancies remained, particularly near the base of the convection zone and close to the surface. These discrepancies would later prove to be critically important. Extending helioseismology to other stars, astroseismology had been a dream for decades but was impossibly difficult from the ground. Solar-like oscillations have amplitudes of only a few parts per million in brightness, far below the noise floor of ground-based photometry. The atmospheric scintillation alone, The twinkling that makes stars appear to twinkle to the naked eye masks these tiny signals completely. Only from space, above the atmosphere, with a continuous monitoring over months or years, could the oscillation frequencies of distant stars be measured. Kepler delivered this capability on an industrial scale. Over its 4-year prime mission, it detected solar-like oscillations in more than 500 main sequence and subgiant stars, measuring individual oscillation frequencies for many of them. For red giant stars, evolved stars with larger radii and therefore longer oscillation periods, making their modes easier to detect. Kepler identified oscillations in more than 15,000 targets. Before Kepler, the total number of stars with precisely measured astroseismic frequencies was fewer than 50. After Kepler, it exceeded 20,000. The field did not advance incrementally. It underwent an explosion. Papers poured out of the Kepler Astroseismic Science Consortium, known as CASC, at a rate that overwhelmed the capacity of traditional peer review. New analysis pipelines were developed, validated against each other, and applied to the growing flood of data. Within just 3 years of the first Kepler data release, astroseismology had gone from a niche specialty practiced by a few dozen theorists and observers to a mainstream tool used by hundreds of researchers across multiple subfields of astrophysics. The red giant results were the crown jewel. Red giants are large enough that their oscillation periods are measured in hours rather than minutes, and their oscillation amplitudes are larger and more easily detectable. More importantly, red giants have a special type of oscillation mode that carries information from the deepest interior of the star, mixed modes. These are oscillations that behave as pressure modes in the outer envelope and gravity modes in the dense, radiative core, coupled together through a region called the evanescent zone. A mixed mode probes both the surface and the core simultaneously, carrying information about conditions that no other observational technique can access. The discovery of mixed modes in Kepler red giants was a watershed moment in stellar astrophysics. For the first time, astronomers could directly measure the rotation rate of a stellar core, not the surface, which is accessible through spectroscopy, but the deep interior, which had been completely inaccessible until that moment. The team led by Paul Beck of KU Leuven, publishing in 2012, detected rotational splitting in the mixed modes of a red giant observed by Kepler and determined that the core was rotating roughly 10 times faster than the envelope. This was unexpected, not because the core was rotating faster, which was predicted, but because it was rotating so slowly. Here is the problem. As a star evolves off the main sequence and its core contracts, conservation of angular momentum should spin the core up dramatically. Think of an ice skater pulling in her arms. The rotation speed increases as the radius decreases. Stellar models predicted that the cores of red giants should be spinning 100 to 1,000 times faster than the envelopes. But the mixed modes showed core rotation rates only about 10 times faster. Something was extracting angular momentum from the cores of these stars with an efficiency that no standard model predicted. What could be removing the angular momentum? The leading candidates include internal gravity waves, oscillations driven by buoyancy in the radiative zone that can transport angular momentum outward as they propagate and break, and magnetic fields threading the stellar interior, which can exert torques that transfer angular momentum between the core and the envelope. But quantitative calculations of both mechanisms have so far fallen short. Internal gravity waves transport some angular momentum, but not enough. Magnetic fields could potentially do it, but the detailed field geometry inside a red giant is unknown and difficult to model. A third possibility involves mixed modes themselves. The very oscillations used to detect the slow rotation may themselves be transporting angular momentum, acting as both the diagnostic tool and the physical agent of angular momentum redistribution. Some theorists have proposed that the interaction between oscillation modes and the differential rotation creates a feedback loop, where the modes extract energy from the shear and redistribute it, gradually spinning down the core. But this mechanism, too, remains quantitatively uncertain. The core rotation problem is not merely an academic puzzle. It has direct consequences for the final fates of stars. The angular momentum retained in a stellar core determines how fast the resulting white dwarf or neutron star will spin. Millisecond pulsars, neutron stars rotating hundreds of times per second, require specific angular momentum histories. And if the angular momentum transport in their progenitor red giants was more efficient than models predict, the standard formation scenarios for these objects may need revision. The oscillations of red giant stars, detected by a space telescope designed to find planets, have thus opened a question that connects the lives of ordinary stars to the physics of the most exotic objects in the universe. And Kepler's revelations did not stop at rotation. The frequency patterns of mixed modes also allow astronomers to distinguish between red giants burning hydrogen in a shell around an inert helium core, stars ascending the red giant branch for the first time, and red giants burning helium in their cores with hydrogen burning in a surrounding shell, stars on the red clump or horizontal branch after the helium flash. These two evolutionary stages overlap in their surface properties: temperature, luminosity, surface gravity, but they differ in their core structures, and the mixed mode patterns betray the difference. The ability to classify red giants by evolutionary state, using nothing but their oscillation frequencies, opened up entirely new avenues for galactic archaeology. Using stellar populations as probes of the formation and chemical enrichment history of the Milky Way. A red giant on the hydrogen shell burning phase is ascending the red giant branch for the first time and has not yet ignited helium in its core. It carries within its composition and kinematics a record of where and when it was born. A red clump star, by contrast, has undergone the helium flash, a violent, brief thermonuclear runaway in its degenerate helium core, and has settled into a more stable phase of core helium burning. The two types occupy different chapters of stellar evolution, and their relative numbers, spatial distribution, and chemical compositions constrain models of how the Milky Way assembled itself over billions of years. Before Kepler, distinguishing these two populations required careful spectroscopic analysis and often remained ambiguous. After Kepler, a single look at the oscillation frequency pattern sufficed. The mixed modes told the story that the surface could not. Chapter 4. TESS and the Survey of the Whole Sky. When the original Kepler mission ended in 2013, after the failure of two of the spacecraft's Cars 4 reaction wheels, which robbed it of the ability to point precisely, the loss was felt across the entire field. But the data Kepler had collected continued to yield discoveries for years afterward, and the spacecraft was ingeniously repurposed as the K2 mission, which observed fields along the ecliptic plane in campaigns of about 75 days each. K2 could not match the 4-year continuous baseline of the original mission, but it surveyed many more fields across the sky, observing pulsating stars in open clusters, globular clusters, and diverse galactic environments. And then, in April of 2018, NASA launched the Transiting Exoplanet Survey Satellite, TESS. Where Kepler had stared at a single patch of sky, TESS was designed to survey nearly the entire sky, dividing it into sectors and observing each sector for about 27 days. Some regions near the ecliptic poles received continuous coverage for nearly a year. TESS's photometric precision was somewhat lower than Kepler's, roughly 10 times less sensitive per unit time, but its all-sky coverage meant that it observed far more SWAR stars, including many bright, nearby targets that Kepler had missed because they lay outside its narrow field of view. For astroseismology, TESS has been transformative in a different way than Kepler. Kepler provided the deepest, most detailed frequency spectra for a moderate number of stars. TESS provides less detailed, but still scientifically valuable oscillation detections for a vastly larger sample. Together, the two missions have mapped the astroseismic properties of stellar populations across the Milky Way, from the thin disk to the thick disk to the halo, providing constraints on stellar ages, masses, and chemical abundances that feed directly into models of galactic formation and evolution. TESS has also observed classical pulsating variables, Cepheids, Ara Lyrae stars, Delta Scuti stars, with its all-sky coverage, adding new data to the characterization of their pulsation properties. For Delta Scuti stars in particular, TESS has revealed a richer and more complex spectrum of oscillation modes than ground-based observations ever detected, challenging theorists to explain why so many modes are excited and how they interact non-linearly. Some Delta Scuti stars observed by TESS show dozens or even hundreds of independent oscillation frequencies, many of which do not correspond to any predicted mode in standard stellar models. This embarrassment of riches, too many modes, not too few, presents a fundamental challenge for astroseismic analysis, because the identification of which observed frequency corresponds to which theoretical mode is a prerequisite for extracting internal structure information, and with hundreds of unidentified modes, the matching problem becomes combinatorially intractable. A breakthrough came in 2020 when Timothy Bedding at the University of Sydney and an international team of collaborators identified a subset of young, rapidly rotating Delta Scuti stars observed by TESS, whose oscillation spectra showed remarkably regular patterns, evenly spaced sequences of frequencies that could be clearly identified as radial, dipole pressure modes. These regular pulsators, as they were called, behaved like textbook oscillators, their frequency patterns matching theoretical predictions almost perfectly. The discovery suggested that the complexity of most Delta Scuti spectra arises not from exotic physics, but from the effects of rapid rotation and mode coupling, which distort the frequency patterns beyond easy recognition. By selecting the simplest, most slowly rotating examples, the field could establish a beachhead of understanding from which to tackle the more complex cases. But TESS also did something that Kepler could not. It observed entire stellar populations simultaneously across the sky. For classical Cepheids, this was invaluable. TESS obtained continuous uniform photometry of nearly every known galactic Cepheid brighter than 12th magnitude, providing a homogeneous dataset that eliminated the systematic differences between instruments, filters, and observing conditions that had plagued ground-based surveys for decades. For the first time, astronomers could compare the light curves of hundreds of Cepheids, measured with the same detector, the same cadence, and the same photometric pipeline. The resulting period luminosity relations, calibrated against Gaia parallaxes, were among the most precise ever constructed for the Milky Way, and TESS is still observing. Its extended mission continues to cycle through the sky, building up longer baselines and detecting fainter oscillation signals. With each pass, the astroseismic census of the Milky Way grows more complete, more detailed, and more powerful. The dream that began with a few radial velocity measurements of a single star, Delta Cepheid, observed by John Goodricke in 1784, has become a systematic survey of stellar interiors across the galaxy. Chapter 4b, The White Dwarf Pulsators, Stellar Graveyards That Still Sing. The story of stellar pulsation does not end when a star dies. White dwarfs, the dense, Earth-sized remnants left behind when low and intermediate mass stars exhaust their nuclear fuel, can also pulsate, and their oscillations reveal the internal structure of these stellar corpses with extraordinary precision. The first pulsating white dwarf was discovered in 1968 by Arlo Landolt, who noticed that the star HL Tauri 76 exhibited brightness variations with a period of roughly 12.5 minutes. Landolt initially suspected an instrumental artifact. The variations were small, barely a few percent in brightness, but repeated observations confirmed that the star was genuinely variable. It took several years before the theoretical explanation emerged. The star was oscillating in non-radial gravity modes, driven by a mechanism similar in spirit to the Kappa mechanism, but operating through the partial ionization of hydrogen or helium in the white dwarf's thin outer envelope. These pulsating white dwarfs were eventually classified into three main families, each corresponding to a different surface composition and effective temperature. The Davy stars, also called ZZ Ceti stars, have hydrogen-rich atmospheres and pulsate, with periods between roughly 100 seconds and 25 minutes at effective temperatures near 11,000 to 12,500 Kelvin. The DBV stars, or V777 Hercules stars, have helium-rich atmospheres and pulsate at higher temperatures, around 22,000 to 29,000 Kelvin, with similar period ranges. The DOV stars, or GW Virginis stars, are the hottest pulsating white dwarfs, with carbon and oxygen-rich atmospheres and effective temperatures exceeding 75,000 Kelvin, occupying a transitional phase between the planetary nebula nucleus stage and the white dwarf cooling track. What makes white dwarf astroseismology so powerful is the simplicity of the underlying structure. A white dwarf is, to a first approximation, a ball of degenerate carbon and oxygen surrounded by thin layers of helium and, in the DA stars, an even thinner layer of hydrogen on top. The gravity modes that these stars exhibit have periods determined primarily by the Brunt-Väisälä frequency profile, a quantity that depends on the density stratification and composition gradients inside the star. Each composition boundary, between the carbon-oxygen core and the helium layer, between the helium layer and the hydrogen layer, acts as a partial reflector for gravity waves, creating characteristic patterns of mode trapping that leave fingerprints in the observed period spectrum. By measuring the periods of a pulsating white dwarf with high precision and comparing them to theoretical models, astroseismologists can determine the total stellar mass, the mass of the hydrogen and helium layers, the core composition ratio of carbon to oxygen, and even the internal temperature profile. The hydrogen layer mass is particularly important because it controls the rate at which the white dwarf cools. A thicker hydrogen layer provides more insulation and slows the cooling, and white dwarf cooling ages are one of the oldest and most reliable clocks in astrophysics. They have been used to date the ages of globular clusters, the galactic disk, and even the age of the universe itself, independently of any cosmological model. One of the most remarkable achievements of white dwarf astroseismology came from sustained monitoring campaigns of individual pulsating white dwarfs over decades, because the oscillation periods of a cooling white dwarf change as the star loses thermal energy, becoming very slightly longer as the temperature drops. It is possible, in principle, to measure the rate of period change and thereby determine the cooling rate directly. The expected period change is extraordinarily small, on the order of 1 second every 100,000 to 1 million years, but with decades of timing data, it becomes measurable. The pulsating white dwarf G117-b15a was monitored for over 30 years, and its measured rate of period change was found to agree remarkably well with theoretical cooling models. This agreement provided a direct, observational confirmation that our understanding of white dwarf cooling physics, including the role of neutrino emission from the core and the crystallization of the carbon-oxygen interior, is fundamentally correct. The crystallization of white dwarf interiors is itself a stunning prediction confirmed by astroseismology and more recently by Gaia. As a white dwarf cools below a critical temperature, roughly 6,000 Kelvin in the core, the dense carbon-oxygen plasma undergoes a phase transition from a liquid to a crystalline solid. The star literally freezes from the inside out, releasing latent heat that temporarily slows the cooling. The Gaia spacecraft's precise parallaxes and photometry revealed an overdensity of white dwarfs in the color magnitude diagram at exactly the luminosity where crystallization is expected to stall cooling, a pile-up of stars spending extra time at that brightness because of the released energy. It was a confirmation of a theoretical prediction first made in the 1960s by Hugh Van Horn, waiting half a century for the observational technology to catch up. But the Gaia data revealed an additional surprise. The pile-up was slightly more pronounced than theoretical models predicted, suggesting that crystallization releases more energy than the latent heat of solidification alone. One proposed explanation involves the gravitational settling of heavier elements, primarily oxygen, toward the center of the white dwarf as the crystal lattice forms. Because the crystallizing material preferentially incorporates oxygen, the remaining liquid above the solidification front becomes enriched in lighter carbon, creating a compositional inversion that drives convective mixing and releases additional gravitational potential energy. This process, called crystallization-driven convection, could delay the cooling of massive white dwarfs by billions of years, fundamentally altering the age estimates derived from white dwarf luminosity functions. The implications are remarkable. If the cooling ages of the oldest white dwarfs in the galaxy are systematically longer than previously thought, then the ages of the oldest stellar populations, and by extension, the age of the galactic disk and halo may need to be revised. Once again, the physics of stellar pulsation and its close cousin, stellar cooling, reach beyond the individual star to touch the largest questions in astrophysics. Chapter 4c. The search for solar gravity modes. Listening for the sun's heartbeat. While astroseismology was transforming our understanding of distant stars, one of the most tantalizing goals in helioseismology remained frustratingly out of reach: the detection of gravity modes in the sun, pressure modes. The acoustic oscillations that helioseismology had exploited so successfully since the 1970s are trapped in the outer convective layers of the sun and carry information, primarily about the outer 30% of the solar interior. But gravity modes, driven by buoyancy forces in the stably stratified radiative zone, would probe the deep core, the innermost 10 to 20% of the solar radius, where hydrogen fusion actually occurs. Detecting solar G-modes would provide direct information about the rotation rate of the solar core, the temperature and composition profile in the nuclear burning region, and potentially even constraints on exotic physics, such as the properties of dark matter particles that might accumulate in the sun's center. The problem is that solar gravity modes, if they exist at the surface, are predicted to have amplitudes of no more than a few millimeters per second in velocity, thousands of times smaller than the pressure modes, which themselves are only centimeters per second. The convection zone acts as a powerful filter, exponentially attenuating gravity waves as they attempt to tunnel through the turbulent, convective outer layers. By the time a gravity mode born in the deep core reaches the surface, its amplitude has been reduced by factors of millions or billions. Numerous claims of solar G-mode detection have been made over the decades, beginning in the 1970s, but none has achieved consensus acceptance. A group led by Raphael Garcia at the French Alternative Energies and Atomic Energy Commission published a paper in 2007 reporting a periodic pattern in the low-frequency region of the solar oscillation spectrum observed by the Gulf instrument on the SOHO spacecraft that they interpreted as the asymptotic signature of dipole gravity modes. The pattern had a characteristic period spacing of approximately 24 minutes, roughly consistent with theoretical predictions, but the signal was at the very edge of detectability, and other groups analyzing the same data with different methods did not reproduce the result convincingly. The search continues. The solar gravity mode detection remains one of the great unresolved challenges in stellar physics, a measurement that, if achieved definitively, would open a window into the most inaccessible region of the nearest star. It is a reminder that even for the Sun, our closest stellar laboratory, the deepest secrets remain hidden behind layers of plasma and turbulence that even the most sensitive instruments struggle to penetrate. The difficulty of detecting solar G-modes also highlights a deeper truth about astroseismology. The information that oscillation modes carry is only as valuable as our ability to detect and correctly identify them. For stars with thin or non-existent convective envelopes, such as the hot, massive beta Cephei variables and the slowly pulsating B stars, gravity modes propagate freely to the surface and are readily observable. These stars have become important laboratories for testing theories of convective overshooting, chemical mixing, and internal rotation in massive stars. The Kepler satellite detected gravity mode period spacings in several dozen slowly pulsating B stars, and the patterns revealed that the convective core boundaries in these stars are not as sharp as classical models assumed. The cores are surrounded by zones of partial mixing, where nuclear-processed material gradually diffuses outward, altering the chemical composition profile and affecting the star's subsequent evolution. This result has profound implications for our understanding of how massive stars live and die. The extent of mixing near the convective core determines how much hydrogen fuel is available for nuclear burning, and therefore how long the star lives on the main sequence. A star with more mixing lives longer, reaches higher luminosities, and produces a different remnant, a more massive white dwarf, neutron star, or black hole, than an identical star with less mixing. Gravity modes, by probing the mixing zones directly, are providing the constraints that stellar evolution models have needed for decades, but could never obtain from surface observations alone. Chapter 4D: Ensemble Astroseismology and Galactic Archaeology. Stars as fossils of the Milky Way, perhaps the most far-reaching consequence of the Kepler and TESS astroseismology revolutions, has nothing to do with the stars themselves. It has to do with the galaxy they inhabit. Every star carries within its oscillation frequencies a record of its mass, radius, surface gravity, and, through the scaling relations that connect oscillation properties to fundamental stellar parameters, its age. A star's mass, combined with its chemical composition, determines how quickly it evolves. A star with twice the mass of the Sun exhausts its core hydrogen roughly 8 times faster, giving it a lifespan of only about 1.5 billion years compared to the Sun's roughly 10 billion. By measuring the mass of a red giant through astroseismology and combining it with spectroscopic measurements of its surface composition, astronomers can estimate when that star was born, how many billions of years ago it formed from the interstellar gas. This is galactic archaeology. The idea is to use stars as fossils, relics of the Milky Way's past, to reconstruct the formation history of the galaxy. When was the thick disk formed? When did the thin disk begin to assemble? What was the chemical enrichment history of different regions of the galaxy? Were there ancient merger events that brought in stars from other, now destroyed, satellite galaxies? Before astroseismology, stellar ages were among the most difficult quantities in astrophysics to measure. The standard method, isochrone fitting, which involves placing a star on a theoretical diagram of temperature versus luminosity and finding which evolutionary track it falls on, works well for star clusters where many stars of the same age can be fit simultaneously, but is notoriously imprecise for individual field stars. Uncertainties of 30 to 50% were common, and systematic errors from uncertain distance measurements, extinction, and model physics often exceeded the random uncertainties. Astroseismology changed this calculus dramatically. For red giants observed by Kepler, astroseismic masses could be determined with precisions of roughly 5 to 10%, which translates to age precisions of 20 to 30% for stars in the right mass range. Still not perfect, but an enormous improvement over isochrone fitting alone. When combined with detailed chemical abundance measurements from ground-based spectroscopic surveys, such as APOGI, the Apache Point Observatory Galactic Evolution Experiment, which measured abundances of up to 25 chemical elements for hundreds of thousands of stars across the Milky Way. The results were transformative. The APOCAS catalogue, a collaboration between apogee spectroscopy and Kepler astroseismology, provided masses, radii, ages, and detailed chemical compositions for thousands of red giants in the Kepler field. This catalogue revealed clear age metallicity relations in the galactic disk, confirmed that the thick disk is older and more metal-poor than the thin disk, and identified chemically peculiar stars that may have been accreted from satellite galaxies during ancient merger events. One of the most striking results was the discovery that the alpha element-rich thick disk stars span a narrow range of ages, roughly 8 to 12 billion years, suggesting that the thick disk formed rapidly in a burst of star formation early in the Milky Way's history, possibly triggered by a major merger event. With TESS extending the astroseismic survey to the entire sky, and future missions like the European Space Agency's Plato planned for launch in 2026, promising even more precise and extensive astroseismic data, the Galactic Archaeology program is entering a golden age. Plato will observe hundreds of thousands of stars in long-duration pointings with photometric precision comparable to Kepler, specifically targeting bright stars with known planetary systems. The combination of precise stellar ages, chemical compositions, and planetary system architectures will allow astronomers to study not just how the galaxy formed, but how planetary systems formed and evolved within it, connecting the history of stars to the history of worlds. The pulsations of variable stars, once curiosities observed by amateur astronomers peering through backyard telescopes, have become one of the most powerful tools in modern astrophysics. From Goodrich's notebook in York to the terabytes of space telescope data streaming down from orbit, the thread is unbroken. Light changes. We measure the changes. and from those measurements, we reconstruct the hidden architecture of the cosmos. Chapter 5. Polaris. The North Star's deepening mystery. Of all the variable stars in the sky, none carries more cultural weight than Polaris, the North Star. It is the pivot point of the northern sky, the star by which mariners have navigated for centuries, the anchor of the celestial sphere's apparent rotation. It is also, as astronomers have known for more than a century, a Cepheid variable, the nearest and brightest Cepheid visible from Earth, at a distance of roughly 430 light-years. Its pulsation period is just under 4 days, 3.97 days, and its variability was confirmed spectroscopically by Ejnar Hertzsprung in 1911. But Polaris is not a well-behaved Cepheid. It is, in fact, one of the most puzzling. For most of the 20th century, Polaris's pulsation amplitude was declining steadily. Early observations indicated a radial velocity amplitude of roughly 5 to 6 kilometers per second before 1950. By the mid-1980s, the amplitude had dropped to around 1.5 kilometers per second. By the early 1990s, it had fallen to a barely detectable 0.5 kilometers per second, so small that a 1994 paper was titled "Goodbye Polaris the Cepheid," predicting that the pulsations would stop entirely and the star would exit the instability strip. Then Polaris surprised everyone. By the late 1990s, the amplitude began to increase again. The star that was supposed to stop pulsating had reversed course. By 2015, the radial velocity amplitude had climbed back to roughly 4.2 kilometers per second. Photometric observations confirmed the trend. The brightness variation, which had shrunk to about 20 millimagnitudes, was growing. But then, in 2017 and 2018, new high-precision spectroscopic measurements revealed another reversal. The amplitude dropped again, falling to about 2.8 kilometers per second. The pulsation was waxing and waning in a pattern that no simple model of stellar evolution across the instability strip could explain. Meanwhile, the pulsation period itself was changing. For most of the 20th century, it had been increasing at a rate of about 4.5 seconds per year, consistent with a star evolving redward across the instability strip as its radius and luminosity slowly increased. But recent observations suggest the period may have stopped increasing and possibly begun to decrease, which would imply a change or even a reversal in the star's evolutionary direction. What is causing these erratic changes? One compelling explanation emerged from careful analysis of Polaris's binary nature. Polaris is not a single star, it is a member of a triple system. The faint visual companion Polaris B orbits at a large separation, visible through modest telescopes. But there is a much closer companion, Polaris AB, that orbits the Cepheid with a period of about 29.6 years in an eccentric orbit. Recent spectroscopic work by Guillermo Torres at the Center for Astrophysics at Harvard has shown that the changes in Polaris's pulsation amplitude may correlate with the orbital motion of this close companion. When Polaris AB approaches its closest distance to the Cepheid during each orbital passage, it gravitationally perturbs the outer layers of the pulsating star, precisely the layers where the Kappa mechanism operates. This perturbation modulates the pulsation amplitude on a timescale linked to the orbital period. If this interpretation is correct, it means that even the most basic observable of a Cepheid, its pulsation amplitude, can be altered by the gravitational influence of a companion star, and Polaris is far from unique in having companions. Studies using the Hubble Space Telescope have found that roughly 80% of Milky Way Cepheids have at least one companion within a few arcseconds. Some of these companions are close enough to interact gravitationally with the Cepheid's pulsation. Others contribute unresolved light that can bias the measured brightness and therefore the inferred distance. Polaris also shows evidence for a circumstellar envelope, a shell of gas 2 to 3 times the size of the star itself, detected through infrared excesses and spectroscopic anomalies. This envelope may consist of material ejected by the Cepheid's own pulsation. As the star's surface moves outward at velocities of up to 100,000 kilometers per hour during each pulsation cycle, some fraction of the gas at the outermost boundary may escape the star's gravitational pull. Over time, this material accumulates into a diffuse shell, Circumstellar envelopes have been detected around several other Cepheids as well, including L Carinae and Delta Cephei itself, and their presence raises the question of whether they affect the infrared brightness of the star and therefore the period luminosity relation at infrared wavelengths. The infrared period luminosity relation has long been considered more reliable than the optical one because infrared observations are less affected by interstellar extinction, the dimming and reddening of starlight, by dust grains along the line of sight. But if Cepheids are surrounded by their own locally produced dust and gas, the infrared brightness could be systematically affected in ways that depend on the pulsation amplitude, the mass loss rate, and the viewing geometry. This is not a small concern. Even a systematic bias of a few percent in Cepheid infrared magnitudes would propagate directly into the distance ladder and could shift the inferred value of the Hubble constant by an amount comparable to the current tension between local and cosmic microwave background measurements. Recent interferometric observations using the VLTI, the Very Large Telescope Interferometer at the European Southern Observatory in Chile, have spatially resolved the circumstellar envelopes around several nearby Cepheids, confirming their existence and measuring their angular sizes. The envelopes are typically 2 to 3 stellar radii in extent and contribute between 1 and 10% of the total flux in the near-infrared K-band. Correcting for this excess emission is now an active area of research, with groups developing models that self-consistently predict the mass loss rate, envelope structure, and infrared excess as functions of the pulsation properties. The story of Polaris is a microcosm of the broader challenge facing variable star astronomy. The more closely we examine any individual star, the more complexity we find. Binary companions, circumstellar material, nonlinear, pulsation dynamics, mode switching, all of these effects introduce scatter and potential bias into the clean, elegant relationships that make variable stars useful as distance indicators. The challenge is not to eliminate the complexity, that is impossible, but to understand it well enough to account for it, to model it, and to include it in the error budget of every distance measurement. Variable stars have never offered easy answers. What they offer is something more valuable, the right questions, and those questions about the internal structure of stars, about the physics of pulsation, about the expansion rate of the universe, are more important now than at any point in the past century. The next discovery would make even this look small. What variable stars have revealed, across more than 2 centuries of observation, is not a single discovery, but a cascade of them, each one building on the last, each one rewriting what we thought we knew about the universe. The first revelation was geometric. Henrietta Leavitt's period luminosity relation transformed variable stars from curiosities into cosmic rulers, giving astronomers a way to measure distances that no parallax could reach. That single relationship, brighter Cepheids pulse more slowly, unlocked the scale of the universe. It proved that the Milky Way was not alone, that the spiral nebulae were galaxies in their own right, that the cosmos was vastly larger than anyone had imagined. Without Leavitt's law, Hubble could not have measured the distance to Andromeda. Without that distance, the expanding universe might have remained hidden for decades. The second revelation was physical. The Kappa mechanism showed that stellar pulsation is not a mystery, but a consequence of known physics. The interaction between radiation and partially ionized helium, operating as a thermodynamic valve deep inside the stellar envelope. This was not merely an explanation of why Cepheids pulsate. It was a demonstration that the interiors of stars, though forever hidden from direct view, obey the same laws of thermodynamics and radiative transfer that physicists study in their laboratories. The pulsation of a star is a message from the interior, encoded in the rhythm of the light curve, waiting for someone with the right physics to decode it. The third revelation was structural, astroseismology, the measurement and interpretation of stellar oscillation frequencies, turned that encoded message into a detailed blueprint. The oscillation modes of a star carry information about its internal sound speed, density profile, chemical composition gradients, core rotation, and evolutionary state. Before astroseismology, stellar interiors were theoretical constructs, models constrained by surface observations and nuclear physics, but never directly tested. After Kepler and TESS, stellar interiors became observable. The rotation of a red giant's core, the crystallization of a white dwarf's interior, the mixing zones around a massive star's convective core, all of these previously hidden features became accessible through the patient analysis of stellar light curves. And the fourth revelation is cosmological, and it is still unfolding. The Hubble tension, the persistent, statistically significant disagreement between the local measurement of the universe's expansion rate and the value inferred from the cosmic microwave background, may be telling us that something fundamental is missing from our cosmological model. Variable stars, through their role in the distance ladder, are at the center of this disagreement. Every improvement in our understanding of Cepheid pulsation physics, every refinement of the period luminosity relation, every correction for metallicity and crowding and circumstellar envelopes pushes toward a resolution, or confirms that the tension is real and that new physics is required. This is not science fiction. This is the actual state of modern astrophysics, in which the brightness changes of stars, first noticed by amateur observers in the 18th century, are now driving the most consequential debates in fundamental physics. The same phenomenon, a star getting brighter and dimmer in a regular pattern, connects John Goodrick's observations of delta Cephei in 1784 to the question of whether the standard model of cosmology needs to be revised in 2026. What does it mean that we can listen to the interiors of stars? It means that the boundary between the known and the unknown has shifted. For most of human history, stars were points of light, beautiful, unreachable, and fundamentally mysterious. Even after spectroscopy revealed their chemical compositions and photometry measured their brightnesses, the interiors remained terra incognita. We could model them, calculate them, predict them, but we could not observe them directly. The sun was a surface. Every other star was less than a surface, a dot. Astroseismology has changed this. When we measure the oscillation frequencies of a red giant and determine that its core is rotating 10 times faster than its envelope, we are not making an inference from a model. We are making a measurement. The mixed modes carry the signature of the core rotation directly to the surface, encoded in the splitting of frequency peaks, readable by anyone with the right data and the right analysis tools. This is observational astrophysics at its most powerful, using the natural vibrations of a physical system to probe its hidden structure in exactly the same way that geophysicists use earthquake waves to map the Earth's interior, or that physicians use ultrasound to image a developing fetus. The analogy to medicines is not merely poetic. In both cases, the oscillations are non-invasive. They do not disturb the system they probe. In both cases, the information is encoded in the frequency spectrum, the pattern of peaks and their spacing, splitting, and amplitudes. And in both cases, the interpretation requires sophisticated models that connect the observable frequencies to the underlying physical structure. The difference is scale. A medical ultrasound probes a volume measured in cubic centimeters. An asteroseismic analysis probes a volume measured in cubic solar radii, 1 billion cubic kilometers for a typical red giant. But the implications reach further than stellar physics. The ages that astroseismology provides are feeding into models of galactic formation and evolution. The mixing parameters it constrains are revising our predictions of how stars produce and distribute the heavy elements, carbon, nitrogen, oxygen, iron, that make up planets, oceans, and living organisms. The core rotation rates it measures are shaping our understanding of how angular momentum is transported through stellar interiors, which in turn determines the spins of the white dwarfs, neutron stars, and black holes that stars leave behind when they die. And the Hubble tension, if it is real, may force a revision of the standard cosmological model that has served as the foundation of physical cosmology for a quarter century. The lambda CDM model, cold dark matter with a cosmological constant, has been extraordinarily successful at explaining the large-scale structure of the universe, the cosmic microwave background, the abundance of light elements, and the accelerating expansion. But if the Hubble constant measured locally is genuinely and irreducibly different from the value predicted by the model, then something in the model is wrong. Perhaps dark energy is not a constant. Perhaps the early universe contained a component, early dark energy, extra relativistic species, a phase transition that the current model does not include. Perhaps the very framework of general relativity requires modification on cosmological scales. Variable stars cannot answer these questions alone, but they are essential to asking them correctly. The precision of the local Hubble constant measurement depends on the precision of the Cepheid distance ladder, which depends on the precision of the period luminosity relation, which depends on our understanding of stellar pulsation physics. Every link in this chain is forged from the study of variable stars. Pull out any one link, and the entire argument collapses. In 1784, a 19-year-old Englishman who could neither hear nor speak sat in the cold night air of York, watching a star grow brighter and dimmer over a period of 5 days. He recorded his observations with the care and precision of a born scientist, noting the times, the comparison stars, and the rhythm of the variation. He did not know that the star, Delta Cephei, was pulsating. He did not know that its pulsation was driven by the partial ionization of helium in a thin layer deep beneath its visible surface. He did not know that the relationship between its period and its luminosity would one day be used to measure the distance to galaxies millions of light years away. He knew only that the star changed, and that the change was regular, and that regularity in nature demands explanation. John Goodricke died 2 years later, at the age of 21, probably of pneumonia contracted during his long nights of observation. He never learned what his discovery would become. He never saw the chain of understanding that would extend from his notebook to Henrietta Leavitt's glass plates, to Edwin Hubble's photographic observations, to the Kepler Space Telescope's digital data streams. He never imagined that the rhythm he had measured, 5 days, 8 hours, 47 minutes, would echo through 2.5 centuries of scientific progress, touching every major question about the scale, structure, and fate of the universe. But that is exactly what happened. The pulsation of a single star, noticed by a single observer, opened a door that has never closed. Through that door, we learned that the universe is larger than anyone imagined, that it is expanding, that the expansion is accelerating, and that something, dark energy, or something stranger still, is driving that acceleration. Through that door, we learned that the interiors of stars are not theoretical abstractions, but observable realities, accessible through the patient measurement of oscillation frequencies. Through that door, we learned that stars are not merely objects in the sky, but laboratories of physics, engines of chemistry, and archives of history, each one carrying within its pulsations a record of its birth, its life, and its eventual death. The variable stars are still there, still pulsating, still sending their coded messages across the light years. Delta Cephei still brightens and dims every 5.37 days, as it has for millennia, as it will continue to do for millennia more. Polaris still flickers with its enigmatic, waxing and waning amplitude, its companion star tugging gently at the layers where the Kappa mechanism hums. The RR Lyrae stars in the galactic halo still trace the ancient structure of the Milky Way, fossils of a younger galaxy embedded in the older one we inhabit today. The Mira variables still shed their outer layers into the interstellar medium, enriching the raw material from which future stars and planets, and, perhaps, living creatures will someday form. We are, in a sense, the children of variable stars. The carbon in our bodies was forged in stellar cores, dredged to the surface by convective mixing, and expelled into space by the pulsation-driven mass loss of aging giant stars. The oxygen we breathe was synthesized in the nuclear furnaces of massive stars and scattered across the galaxy by supernovae. The iron in our blood was built up through successive generations of stellar nucleosynthesis, each generation enriching the interstellar medium with heavier elements, each generation contributing to the chemical complexity that eventually made planets like Earth and organisms like us possible. When we study variable stars, we are not studying something remote and disconnected from our existence. We are studying the processes that created us. We are reading the autobiography of the universe, written in the language of light and rhythm and change. And the most remarkable thing about that autobiography is that it is still being written. In the pulsations of Cepheids, in the oscillations of red giants, in the crystallizing interiors of white dwarfs, in the unresolved tension between two measurements of how fast the cosmos is flying apart. Let that sink in. The universe is telling us something, and we are learning to listen.